The closest star to our Sun is trying to kill its planets. Right now, 4.24 light-years from the chair you are sitting in, a dim red eye is ticking away in the southern sky. Its name is Proxima Centauri. For over a century, we thought of it as our greatest cosmic neighbor, a quiet companion star just a short hop across the void. When astronomers found a planet there in 2016, orbiting right inside the habitable zone, the internet lit up with hope. Headlines screamed about Earth's twin next door. Scientists talked cautiously but optimistically about liquid water, temperate zones, the tantalizing possibility of life closer than we ever dared imagine. Then the telescopes looked closer. What they found was not a haven. It was a furnace. Proxima Centauri does not burn gently. Every single day, this star erupts in superflares, 10 times more powerful than anything our Sun has ever produced. It bathes its so-called habitable planet in 250 times the X-ray radiation that Earth receives. The surface, tidally locked in place, roasts on one side and freezes on the other, caught in an eternal twilight with nowhere to hide. This is not a world you would want to visit. This is not a star you would want to orbit. And yet, Proxima Centauri is not some distant horror at the edge of the galaxy. It is our front door neighbor, and it is not alone. 70% of all stars in the Milky Way are red dwarfs just like it. Violent, long-lived, hostile to anything fragile enough to call itself life. So how do we square that with the search for life beyond Earth? What does it mean that the universe placed our nearest star within reach, but made it a nightmare? And is there any chance, any possibility at all, that something could survive there? This is that story. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. 4.24 light-years. That's the distance between you and the nearest star that isn't the Sun. Measured in human terms, that's about 40 trillion kilometers, about 25 trillion miles, a distance so enormous that if you could somehow board a commercial airliner and fly straight toward it at cruising speed, you would arrive in roughly 5 million years. Your great-great-great-grandchildren, generations deep into a bloodline that hasn't even begun, would still be mid-flight. And yet, in cosmic terms, 4.24 light-years is nothing. It's next door. It's close enough that astronomers routinely refer to it as our nearest stellar neighbor. Close enough that when humanity started seriously thinking about interstellar travel, this star, Proxima Centauri, became the automatic first candidate, the obvious destination, the place we would go if we ever figured out how to leave. For decades, Proxima Centauri sat in that category of objects astronomers knew about but didn't think much about. It was discovered in 1915 by a Scottish astronomer named Robert Innes, working at the Union Observatory in Johannesburg. Innes was comparing photographic plates of the southern sky, looking for stars that had shifted position between exposures. Proper motion, they call it. The slight apparent drift of a star across the sky over time, caused by its actual movement through space. He found a faint red dot sitting near Alpha Centauri, the bright binary star system that had been known since antiquity. When he measured the parallax, the tiny shift in the star's position as Earth moved around the Sun, he realized this dim red object was even closer than Alpha Centauri itself. It was the nearest star to our solar system anyone had ever found. And for most of the 20th century, that was its claim to fame. Closest star, faint, red, unremarkable. You couldn't see it with your naked eye. It was too dim, still is. If you went outside tonight and looked toward the constellation Centaurus, which is only visible from the southern hemisphere, you would see Alpha Centauri glowing clearly. Proxima would be invisible, a telescope star, a data point. It didn't spark the imagination the way bright stars do. Nobody wrote poems about it. It didn't anchor any constellations. It was just there, ticking along in the dark, doing whatever dim red stars do. Then in August 2016, everything changed. A team of astronomers working with the European Southern Observatory announced they had found a planet orbiting Proxima Centauri. Not a gas giant, not a scorched rock hugging the star at lethal proximity. An Earth-sized world sitting inside what astronomers cautiously refer to as the habitable zone, the range of distances from a star where liquid water could theoretically exist on a planet's surface. They called it Proxima b, and the announcement didn't just make headlines, it detonated them. The closest known exoplanet to Earth, potentially habitable, orbiting the nearest star. It felt like the universe had handed humanity a gift, wrapped in a bow made of probability. For years, scientists had been finding exoplanets around distant stars, hundreds of them, thousands eventually. But they were all far away, dozens, hundreds, even thousands of light-years distant. Proxima b was right here, 4.24 light-years. Still impossibly far by human standards, but close enough that serious people started talking seriously about sending probes. The Breakthrough Starshot initiative, backed by Stephen Hawking and funded by billionaire Yuri Milner, had already proposed using laser-pushed light sails to send tiny spacecraft to Alpha Centauri at a fraction of the speed of light. With Proxima b in the picture, that plan suddenly had a destination with stakes, not just a flyby of a star system, but a close look at a potentially habitable world. The optimism was real. You could feel it in the press releases, in the conference talks, in the way scientists who are normally careful with their language allowed themselves to speculate. Maybe there's water, maybe there's an atmosphere. Maybe, just maybe, something is alive there. Proxima Centauri became humanity's best shot at finding life beyond Earth, within reach of our current understanding of physics. Not tomorrow, not next year, but within the realm of what could be imagined without invoking warp drives or wormholes. The habitable zone calculation was straightforward. Proxima Centauri is a red dwarf, a star much smaller and cooler than our Sun. It's about 12% the Sun's mass, 14% its radius, with a surface temperature hovering around 3,000 degrees Celsius. Compare that to the Sun's nearly 6,000 degree surface. Proxima is dim. It puts out only about 0.17% of the Sun's luminosity. Most of that energy comes out in the infrared rather than visible light. For a planet to be warm enough to have liquid water around a star that faint, it needs to orbit much closer than Earth does to the Sun. Proxima b orbits its star every 11.2 days. That's not a typo. A year on Proxima b lasts 11 Earth days. The planet sits at a distance of about 0.048 astronomical units from its star. 1 astronomical unit is the distance from Earth to the Sun, roughly 150 million kilometers. Proxima b orbits at about 7 million kilometers from Proxima Centauri. For reference, Mercury, the closest planet to our Sun, orbits at about 58 million kilometers. Proxima b is 8 times closer to its star than Mercury is to ours. At that distance, the planet receives roughly the same amount of energy from Proxima Centauri that Earth receives from the Sun. The math worked. The temperatures, at least on paper, looked compatible with liquid water. The discovery was the result of years of painstaking observation using a technique called radial velocity. As a planet orbits a star, its gravity tugs on the star ever so slightly, causing the star to wobble. That wobble shifts the star's light toward the blue end of the spectrum as it moves toward us, and toward the red as it moves away. The shift is tiny, but spectrographs are sensitive enough to detect it. The team used an instrument called HARPS, the High Accuracy Radial Velocity Planet Searcher, mounted on a telescope in Chile. They watched Proxima Centauri for years, measuring its wobble, filtering out noise, accounting for the star's own activity. The signal they found was consistent with a planet roughly 1.3 times Earth's mass pulling on the star every 11.2 days. The announcement in 2016 was careful. The scientists didn't claim they'd found a second Earth. They said they'd found an Earth-mass planet in the habitable zone of the nearest star. That's not the same thing. But the media and the public heard what they wanted to hear. Potentially habitable became Earth-like, became maybe there's life there. The gap between those statements is enormous, but hope has a way of closing gaps that science hasn't. And for a while, hope was winning. Then the observations got better, and hope started losing. The first clue that Proxima Centauri might not be the gentle neighbor everyone wanted it to be came from the star's classification, M5.5 VE. The M means it's a red dwarf. The 5.5 indicates it's on the cooler, dimmer end of the red dwarf spectrum. The V means it's a main sequence star, still fusing hydrogen in its core. The E is the problem. That lowercase e stands for emission lines in its spectrum, a marker that the star has an active chromosphere. In plain language, that means Proxima Centauri is magnetically active. It has a temper. Red dwarfs are not calm stars. They might be small, they might be dim, but many of them are violent. Their magnetic fields twist and snap. Their surfaces erupt in flares, and because they're so small and dense, those flares can be proportionally much more powerful than anything the sun produces. Astronomers had known this about red dwarfs in general for years, but Proxima Centauri specifically hadn't been studied in enough detail to know just how bad its temper was. That changed in early 2017. A team using the Hubble Space Telescope and the Chandra X Ray Observatory turned their instruments toward Proxima Centauri and watched. What they saw was not reassuring. On March 24, 2017, Proxima Centauri unleashed a superflare. The star's brightness increased by a factor of 68 in just a few seconds. The flare released energy equivalent to about 10% of the total energy the sun emits in an entire year, compressed into a matter of minutes. The burst was detected across multiple wavelengths: optical, ultraviolet, X-ray. It wasn't a small event. It was the kind of eruption that, if it happened on our sun, would almost certainly trigger widespread power grid failures, satellite damage, and auroras visible at the equator. For a planet sitting as close to Proxima Centauri as Proxima b does, the effect would be catastrophic. Radiation at those intensities doesn't just warm a planet, it strips atmospheres, it breaks apart molecules, it renders surfaces sterile. The flare lasted for about 10 minutes before settling back to baseline, but the star didn't calm down. Follow-up observations over the next several years detected more flares, lots of them. Proxima Centauri erupts regularly. Some flares are smaller, some are larger, but the star never stays quiet for long. The X-ray flux that Proxima b receives from its star during these flares can spike to levels 4,000 times higher than what Earth receives from the sun under normal conditions. Even during quiet periods, the planet is bathed in X-ray and ultraviolet radiation roughly 100 to 250 times more intense than what Earth experiences. Let that sit for a moment. Proxima b, the closest potentially habitable exoplanet, sits in a radiation environment that would make Earth's surface look like a spa by comparison. Any atmosphere the planet might have had when it formed has likely been blasted away over billions of years of relentless bombardment. Any water on the surface would have been split into hydrogen and oxygen by ultraviolet light, with the hydrogen escaping into space. What's left, if anything, is probably a barren rock with no air, no water, and no chance of supporting life as we understand it. This was not the narrative anyone expected in 2016. The discovery of Proxima b was supposed to be the beginning of a hopeful story. Closest exoplanet, habitable zone, potential for life. Instead, it became a case study in how a star can lie to you. Proxima Centauri looks quiet because it's dim. Its flares don't light up the night sky. Its radiation doesn't reach Earth in any harmful way. From our perspective, it's a faint red dot that you need a telescope to see, but up close, it's a monster. The realization didn't come all at once. It accumulated slowly as more telescopes turned toward Proxima Centauri and more data piled up. Each new observation added another piece to the picture, and the picture that emerged was of a star that had no business hosting a habitable world. The term habitable zone started to feel misleading, technically accurate, but only in the narrowest sense. Yes, Proxima b orbits at a distance where liquid water could exist if everything else were perfect, but everything else is not perfect. The star is a flare machine. The planet is likely tidally locked, meaning one side permanently faces the star while the other is locked in eternal darkness. The magnetic field, if the planet even has one, would need to be extraordinarily strong to fend off the constant onslaught of charged particles from the star. And even then, it might not be enough. By 2018, the scientific consensus had shifted. Papers started appearing with titles like The Habitability of Proxima Centauri b, Environmental States and Observational Discriminants, and Stellar Activity and Erosion of Planetary Atmospheres. The tone was cautious, clinical, but the message was clear. Proxima b is probably not habitable. It might have been once, billions of years ago, before the star's flares stripped it bare. But today it's likely a dead world. The optimism that greeted the discovery in 2016 had curdled into something else. Not despair exactly. Scientists don't do despair, but a kind of resigned acknowledgement that the universe doesn't hand out gifts. It hands out puzzles, and some puzzles have disappointing answers. There's a painful irony in all of this. Humanity spent centuries wondering if we were alone. We built telescopes, launched satellites, scanned the skies for signals, and found nothing. Then we finally discovered the closest exoplanet, one that checked all the boxes for potential habitability, and it turned out to be a radiation-soaked hellscape orbiting a star that throws tantrums. The universe's idea of a joke, maybe, or a reminder that proximity doesn't guarantee hospitality. Proxima Centauri is still our nearest stellar neighbor. That hasn't changed. It's still the star we're most likely to visit first if we ever develop the technology to leave the solar system. But the dream of finding life there, or even finding a world we could one day stand on, has dimmed considerably. What replaced it is a different kind of interest. Proxima Centauri has become a laboratory for understanding red dwarfs, the most common type of star in the galaxy. There are billions of them. If red dwarfs are all as violent as Proxima, then the number of truly habitable worlds in the universe might be far smaller than we hoped. On the other hand, if life can somehow survive around a star like Proxima, clinging to existence in caves or deep oceans or under thick ice, then the universe might be far stranger and more resilient than we imagined. The star hasn't finished surprising us. In 2020, astronomers announced the possible detection of a second planet, Proxima c, orbiting much farther out. The signal is still tentative, not yet confirmed, but if it's real, it would be a super-Earth on a much longer orbit, well outside the habitable zone. Cold, distant, but at least spared the worst of the star's fury. Then in 2022, a third candidate appeared in the data, Proxima d, potentially smaller than Earth, orbiting even closer than Proxima b. The system, it seems, is not simple, which makes sense. Nothing about Proxima Centauri has turned out to be simple. From a distance of 4.24 light-years, Proxima Centauri looked like the answer to one of humanity's oldest questions. Are we alone? Is there another world out there close enough to reach, where life might have taken hold? The star seemed to offer that possibility, a dim, quiet neighbor with a planet in just the right place. But distance, as it turns out, is deceptive. What looks calm from far away can be chaos up close. And Proxima Centauri, for all its proximity, for all the hope it inspired, has proven to be one of the most hostile environments we've ever studied. The red dwarf that seemed like our best bet has become our clearest warning. That's where the story stands now. Not at the beginning, where discovery and excitement lived. Not at the end, because we're still learning. But somewhere in the uncomfortable middle, where the data has piled up and the conclusions are hard to ignore. Proxima Centauri is close, Proxima b is real, and both of them are probably lethal. The star sits out there, 4.24 light-years away, erupting in flares we can't see with our eyes, bathing its planets in radiation we can only measure with our most sensitive instruments. It's been doing this for billions of years. It will keep doing it for billions more. And every flare, every burst of X-rays, every pulse of ultraviolet light is a reminder that the universe doesn't care about our hopes. It operates by rules that predate hope, that will outlast it. Proxima Centauri is teaching us those rules, one violent eruption at a time. The star doesn't warn you before it erupts. There's no build-up you could detect from a distance, no dimming, no cosmic alarm bell. One moment Proxima Centauri is sitting there doing what dim red stars do, radiating faintly in the infrared, barely putting out enough light to register on anything but the most sensitive instruments. The next moment it explodes, not literally. The star doesn't blow apart. But the surface convulses, magnetic field lines snap like overstressed cables, and a torrent of energy blasts outward into space, carrying enough power to rewrite the rules for every object within reach. If you were watching from Earth, with the right telescope pointed at the right patch of sky at the right moment, you would see the star's brightness spike by a factor of 60, 70, sometimes more than 100 in the span of seconds. Then, over the course of minutes or hours, it would fade back to baseline as if nothing had happened. Proxima Centauri would return to being a faint red dot, unremarkable, invisible to the naked eye. And a day or two later, it would do it again. These are not rare events. They are not freak occurrences triggered by unusual circumstances. They are routine. Proxima Centauri throws superflares the way our sun throws light. Constantly, reliably, with a frequency that makes the word active feel like an understatement. Between 2016 and 2020, astronomers catalogued dozens of major flares from Proxima Centauri using a combination of ground-based telescopes and space observatories. Some of the flares were detected in visible light, others showed up in ultraviolet or X-ray wavelengths. A few were caught simultaneously across multiple instruments, giving researchers a complete picture of the event from start to finish. What that picture revealed was a star operating at the edge of what stellar physics predicts is possible for an object its size. To understand what makes Proxima's flares so extreme, you first need to understand what a stellar flare actually is. Stars are not solid. They are balls of plasma, ionized gas held together by gravity and powered by nuclear fusion in their cores. The Sun, for example, fuses hydrogen into helium at its center, releasing energy that works its way outward over the course of hundreds of thousands of years before finally radiating into space as light and heat. But the surface of the Sun, the photosphere, is not a calm place. It churns, it boils. Convection currents drag hot plasma up from below, cool it at the surface, and pull it back down in a constant cycle. And woven through all of that motion are magnetic fields. Magnetic fields on the Sun are generated by the movement of charged particles inside the star. The Sun rotates, dragging its magnetic field lines along with it, twisting them, stretching them, tangling them into increasingly complex shapes. Where those field lines get twisted too tightly, they can snap. When they do, the energy stored in the magnetic field is released all at once in a process called magnetic reconnection. That sudden release of energy heats the surrounding plasma to tens of millions of degrees and accelerates particles to near light speed. The result is a solar flare, a burst of radiation across the electromagnetic spectrum, from radio waves to gamma rays, all released in a matter of minutes. The largest solar flare ever recorded by modern instruments was the so-called Carrington event in 1859. It was powerful enough to disrupt telegraph systems across Europe and North America, set paper on fire in telegraph offices, and produce auroras visible as far south as the Caribbean. Astronomers estimate it released somewhere around 10 to the 32 ergs of energy. That is a 1 followed by 32 zeros. In more familiar terms, it's roughly equivalent to 10 billion 1 megaton nuclear bombs going off simultaneously. The Sun, at its absolute most violent, can do that once every century or two if we're unlucky. Proxima Centauri does worse, a lot worse. And it does it constantly. The first superflare detected from Proxima Centauri in detail was observed in March 2016 by the Atmosphere-Space Interactions Monitor, or ASAS-AT, a European Space Agency observatory, along with XMM Newton, an X-ray telescope. The flare lasted about 10 minutes from start to finish. During that time, the star's luminosity increased by a factor of 68. The energy released was estimated at 10 to the 33rd ergs, 10 times more powerful than the Carrington event. And this was not a once-in-a-lifetime occurrence for Proxima. It was a Tuesday. Follow-up observations over the next several years confirmed what the initial detection suggested. Proxima Centauri erupts in superflares roughly once every 1 to 2 days. Smaller flares, the kind that would still qualify as major events if they happened on our Sun, occur multiple times per hour. The star is never truly quiet. Even during what astronomers generously call quiescent periods, Proxima's X-ray output is elevated compared to the Sun's. The baseline radiation environment around this star is already hostile before you even account for the flares. Red dwarfs as a class are known for this behavior, but Proxima Centauri is extreme even by red dwarf standards. The reason has to do with the star's internal structure. Our Sun has two distinct layers where energy transport happens. In the core and the inner radiative zone, energy moves outward via radiation, photons bouncing from atom to atom in a slow random walk that takes hundreds of thousands of years. In the outer convective zone, energy moves via convection, hot plasma rising to the surface, cooling, and sinking back down. The boundary between those two zones is where the Sun's magnetic dynamo operates, generating the magnetic fields that power solar flares. Red dwarfs don't have that boundary. They are fully convective. The entire star, from core to surface, churns like a pot of boiling water. That means the magnetic dynamo operates everywhere at once. Magnetic fields are generated throughout the star's volume, twisted and amplified by the convective motion, and the result is a magnetic field structure far more complex and far more unstable than anything the Sun produces. Add to that the fact that red dwarfs rotate faster than Sun-like stars, and you have a recipe for constant magnetic chaos. Proxima Centauri rotates once every 83 days. That might sound slow, but for a star its size and age, it's fast. The rapid rotation winds up the magnetic field like a spring, and when that spring snaps, the energy has to go somewhere. In March 2017, astronomers caught Proxima Centauri in the act again. This time the flare was even larger. The star's brightness jumped by a factor of more than 1,000 in the ultraviolet. The X-ray flux spiked to levels 400 times higher than the star's already elevated baseline. The flare released an estimated 10 to the 34 ergs, 100 times more energy than the Carrington event. If a flare like that had originated from our Sun and Earth, had been in the line of fire, the consequences would have been catastrophic. Power grids across entire continents would have collapsed. Satellites would have been fried. The upper atmosphere would have been ionized to the point where radio communication became impossible. Astronauts on the International Space Station would have received radiation doses high enough to cause acute radiation sickness within hours. For a planet sitting where Proxima b sits, less than 8 million kilometers from its star, the situation is incomparably worse. Earth orbits the Sun at 150 million kilometers. Proxima b orbits Proxima Centauri at roughly 5% of that distance. The intensity of radiation follows an inverse square law. Double the distance and the intensity drops by a factor of 4. Halve the distance and it quadruples. Proxima b is sitting 20 times closer to its star than Earth is to the Sun. That means even during quiet periods, the radiation intensity at Proxima b's location is 400 times higher than what Earth experiences. During a superflare, that number explodes. When Proxima Centauri erupts, the X-ray and ultraviolet radiation hitting Proxima b spikes to levels 10,000 times higher than the worst solar storm Earth has ever faced. 10,000 times. Ultraviolet light at those intensities doesn't just tan, it ionizes, it strips electrons off atoms, it breaks apart molecules. Water vapor in an atmosphere would be photodissociated, split into hydrogen and oxygen. The hydrogen, being light, would escape into space. The oxygen would either be blown away by the stellar wind or react with surface materials and get locked into rocks. Over millions of years, an ocean's worth of water could be lost this way. Over billions of years, the entire atmosphere could be eroded down to nothing. Astronomers ran the numbers. If Proxima b started its life with an Earth-like atmosphere, and if it had Earth-like quantities of water, and if it had no magnetic field to shield it from the stellar wind, then by now, 4.5 billion years after the system formed, the planet would be a barren, airless rock. Even if it did have a magnetic field, even a strong one, it might not be enough. Earth's magnetic field protects us from the Sun's relatively gentle output. Proxima Centauri's output is not gentle. The charged particles accelerated during a superflare carry enough energy to punch through all but the most robust magnetospheres. And generating a strong magnetic field requires a molten metallic core and rapid rotation. Proxima b, being tidally locked with one side always facing the star, probably rotates very slowly. Slow rotation means weak magnetic dynamo. Weak dynamo means weak field. Weak field means no protection. There's a comparison that helps put this in perspective. Imagine standing outside on a sunny day. The sun is shining. You feel warm. You might get a sunburn if you stay out too long, but you're not in immediate danger. That's Earth's radiation environment. Now imagine standing in front of an industrial arc welder with no eye protection, no clothing, nothing between you and the arc. The light is so intense it burns your skin in seconds. Your eyes are damaged instantly. The heat is unbearable. That's closer to what the surface of Proxima b experiences during a superflare. Except the arc welder turns on once or twice a day, lasts for minutes to hours, and there's nowhere to hide. The physics of magnetic reconnection, the process that powers these flares, is well understood in broad strokes but devilishly complicated in detail. When magnetic field lines with opposite polarity are brought together, they can reconnect, snapping into a lower energy configuration and releasing the difference as kinetic and thermal energy. On the Sun, this happens in the corona, the outermost layer of the atmosphere where the magnetic field is tangled and twisted by convective motions below. On Proxima Centauri, it happens more often and more violently because the magnetic field is tangled and twisted everywhere. The star's convective churning doesn't just operate in an outer shell, it operates all the way down to the core. That means there are more opportunities for field lines to collide, more regions where reconnection can occur, and more stored magnetic energy waiting to be released. The energy budget of a superflare is staggering. 10 to the 34th ergs is equivalent to about 10% of the total energy the Sun radiates in an entire year, compressed into 10 minutes. Think about that. The Sun's total luminosity, every photon of light warming every planet and asteroid and comet in the solar system, every second of every day, all year long. Now take 1/10 of that annual output and release it in less time than it takes to boil a kettle. That's a Proxima Centauri superflare. And it's not just the total energy that matters, it's the spectrum. Solar flares release most of their energy in visible and infrared light, with a smaller component in ultraviolet and X-rays. Proxima's superflares, by contrast, dump a huge fraction of their energy into the ultraviolet and X-ray bands. Those are the wavelengths that do the real damage. Visible light warms, infrared heats, ultraviolet ionizes, X-rays penetrate. A planet bathed in X-rays isn't just hot, it's being sterilized at the molecular level. DNA, if any existed, would be shredded. Organic molecules would be broken apart. Even the hardiest extremophiles on Earth, the bacteria that live in nuclear reactor cooling pools, the archaea that thrive in boiling acidic springs, would struggle to survive sustained exposure to the kind of radiation Proxima b endures. There's another effect that doesn't get talked about as much but matters enormously. Stellar flares don't just produce light, they produce plasma. Clouds of charged particles, electrons and protons, accelerated to high speeds and ejected from the star's surface. When those clouds hit a planet, they interact with whatever magnetic field or atmosphere the planet has. On Earth, that interaction produces auroras. Beautiful, harmless, a light show in the polar skies. On a planet with a weak or non-existent magnetic field, the interaction is far less benign. The charged particles slam directly into the upper atmosphere, or, if there's no atmosphere, directly into the surface. They sputter away atoms, they implant themselves into rocks, they chemically alter surface materials. Over geological time, this bombardment can erode an atmosphere faster than volcanic outgassing, or cometary impacts can replenish it. Researchers modeled this process for Proxima b. They started with a hypothetical Earth-like atmosphere, a mix of nitrogen and oxygen with traces of carbon dioxide and water vapor. They assumed the planet had no magnetic field. Then they ran the clock forward, simulating billions of years of exposure to Proxima Centauri's flares and stellar wind. The results were unambiguous. Within a few 100 million years, the atmosphere was gone, completely stripped. The planet was left with surface pressure below 1 millibar, less than 1% of Earth's atmospheric pressure, thin enough that liquid water could not exist. Any oceans that had been there evaporated or were lost to space. What remained was a desiccated husk. Even if you add a magnetic field to the model, one comparable in strength to Earth's, the outcome doesn't improve much. The flares are too frequent and too powerful. The magnetic field deflects some of the particles, but not all. The atmosphere erodes more slowly, but it still erodes. Over billions of years, the result is the same. No air, no water, no life. There is a grim irony in the fact that the nearest potentially habitable exoplanet orbits the nearest star, and that star is one of the worst possible hosts for life. If Proxima Centauri were quieter, if it erupted only as often as the Sun does, once every few decades instead of once every day or two, then Proxima b might have had a chance. The planet might have held onto its atmosphere, water might have pooled on the surface, chemistry might have happened. But the star is not quieter. It is loud, violent, relentless. The observations are not ambiguous. Between 2016 and 2024, Proxima Centauri was monitored almost continuously by multiple telescopes. The Transiting Exoplanet Survey Satellite, or TESS, watched it. The Hubble Space Telescope pointed its instruments at it. Ground-based observatories in Chile and Hawaii tracked it. The data all told the same story. Flares, constantly. Some small, some medium, some enormous. The star never rested. Even when it wasn't actively flaring, its X-ray output was elevated. The radiation environment around Proxima Centauri is not periodic. It is chronic. One of the researchers who has spent years studying Proxima Centauri is Meredith McGregor, an astronomer at the University of Colorado Boulder. In an interview following the detection of a particularly large flare in 2018, she put it plainly: "The flares we are seeing from Proxima Centauri are not just frequent, they are devastating. If you were standing on Proxima b during one of these events, you would be exposed to radiation levels that would be lethal within minutes. There is no safe zone on that planet." The largest flare detected so far occurred in May 2019. The star's brightness increased by a factor of 14,000 in the millimeter wavelength range. 14,000. The flare was so energetic that it was detected by the Atacama Large Millimeter Array, or ALMA, a radio telescope in Chile that normally observes cold gas and dust in distant galaxies. ALMA was not even pointed at Proxima Centauri specifically. The flare was bright enough to show up in the data anyway, an unintended photobomb from a star having one of its routine tantrums. That flare released an estimated 10 to the 35 ergs, 1,000 times more energetic than the Carrington event, 10 times more energetic than the average Proxima superflare. If there were any doubt left about whether Proxima b could be habitable, that flare erased it. You cannot build life in an environment where the sky occasionally explodes with the energy of a billion thermonuclear bombs. Not over billions of years, not when it happens every other day. The frequency is the key. A single large flare, even a devastating one, might be survivable if it happened once in a planet's history. Life is resilient. Bacteria can survive in extreme environments. They can hibernate through harsh conditions. They can repair DNA damage, but they cannot do any of that if the damage keeps coming. If every day or two the radiation spikes to lethal levels, there is no time to recover, no time to adapt, no time to evolve defenses. The environment is not just hostile, it is persistently, unrelentingly hostile. For comparison, the Sun produces superflares, events comparable in energy to Proxima's routine outbursts, roughly once every 1,000 years, maybe once every few thousand. The estimates vary, but the point is the same. Superflares from the Sun are rare. Proxima Centauri produces them daily. The difference in frequency is a factor of hundreds of thousands. That is not a small adjustment to make in your mental model of what a habitable star system looks like. That is a fundamental rethinking. The radiation reaching Proxima b during one of these flares does not just bathe the surface, it penetrates. X-rays and high-energy ultraviolet photons can punch through thin atmospheres, thin layers of rock, even meters of water. If there were subsurface oceans on Proxima b, shielded beneath a thick ice crust like Europa or Enceladus, those oceans might be protected. But Proxima b is not an icy moon. It is a rocky planet orbiting in what should be the habitable zone. If it has any ice, it is likely on the night side, the hemisphere permanently facing away from the star, where temperatures plunge to cryogenic lows. The day side, where the star shines constantly, is a blasted desert. There is one more thing the flares do that rarely gets mentioned in the popular press. They produce radio bursts. Not the kind of radio signals that SETI searches for, coherent narrowband transmissions that could only come from technology. These are broadband bursts, noise across a wide range of frequencies, the electromagnetic scream of a star losing its temper. Some of those bursts are strong enough to be detected from Earth with relatively modest radio telescopes. If there were any civilization on Proxima b trying to do radio astronomy, trying to listen to the cosmos, they would be deafened by their own star. The sky would be full of static. The picture that has emerged from nearly a decade of intensive observation is clear. Proxima Centauri is not a quiet neighbor. It is a stellar bully, pummeling anything within reach with radiation, charged particles, and magnetic chaos. The superflares are not anomalies, they are the norm. The star's violence is not a phase, it is its nature, and every piece of data we have collected points to the same conclusion. Any planet orbiting that star, especially one as close as Proxima b, is not a refuge, it is a target, and the bombardment never stops. The habitable zone was supposed to be the answer. For decades, astronomers searching for life beyond Earth had focused on one deceptively simple question: where in a star system could liquid water exist on a planet's surface? Not ice, not vapor, liquid water. The stuff that pools in oceans and lakes and rivers, the medium where chemistry gets interesting, the solvent that every known form of life depends on. Find a planet in the habitable zone, the argument went, and you've found a place where life could in theory take hold. Maybe not intelligent life, maybe not anything more complex than bacteria, but something, a foothold, a chance. The calculation itself is straightforward enough that you could teach it in a high school physics class. A star puts out a certain amount of energy. That energy spreads outward in all directions, diluting as it goes according to the inverse square law. At some distance from the star, the amount of energy reaching a planet's surface would be just right. Not so much that water boils away, not so little that it freezes solid. Goldilocks territory. The habitable zone. For our Sun, that zone sits roughly between 0.95 and 1.37 astronomical units. Earth orbits at 1 astronomical unit, right in the middle. Venus, at 0.72 astronomical units, is too close. Mars, at 1.5 astronomical units, is arguably too far, though that's debatable depending on how thick an atmosphere you think Mars could have sustained. The point is, the zone exists, it's a real thing. And when exoplanet hunters started finding planets around other stars in the mid-1990s, calculating the habitable zone for each system became standard procedure. Proxima Centauri's habitable zone, given the star's feeble luminosity, sits much closer in. The inner edge is at roughly 0.042 astronomical units. The outer edge is at about 0.082 astronomical units. a narrow band hugging the star tightly where the energy flux matches what Earth receives. Proxima b orbits at 0.04848 astronomical units, smack in the middle of that zone. When the discovery was announced in 2016, that placement was the headline: closest exoplanet, habitable zone, potential for liquid water. The math was clean, the excitement was real, and the math was lying. Not because it was wrong, the calculation was correct. Proxima b does receive roughly the same total energy flux that Earth does. If you added up every photon hitting the planet across all wavelengths, integrated over time, the number would match. But that number hides a problem. Not all photons are created equal. A photon of visible light warms, a photon of infrared heats, a photon of X-ray radiation ionizes, penetrates, destroys, and Proxima Centauri, for all its dimness in visible light, is ferociously bright in X-rays. The X-ray flux reaching Proxima b is not twice what Earth receives, not 10 times, 250 times. During the star's frequent flares, that number spikes into the thousands. This is not a minor detail. This is the detail. The habitable zone concept, as traditionally defined, assumes a star like the Sun, a stable main sequence star that emits most of its energy in the visible and infrared, with X-ray and ultraviolet output kept to a polite minimum by a calm magnetic field. Proxima Centauri is not that star. It emits most of its energy in the infrared, yes, but its X-ray output, relative to its total luminosity, is vastly higher than the Sun's. And because Proxima b orbits so close to its star, 20 times closer than Earth does to the Sun, the inverse square law works against it. The X-ray intensity at Proxima b's location is not just proportionally higher, it is catastrophically higher. To put this in perspective, let's talk numbers. Earth receives about 0.001 watts per square meter of X-ray radiation from the Sun during quiet periods. That's a tiny fraction of the total 1,366 watts per square meter of solar energy hitting the planet. X-rays are almost irrelevant to Earth's energy budget. They contribute nothing to warming the surface. They're absorbed in the upper atmosphere, ionizing a thin layer of gas 100 kilometers up, creating the ionosphere, convenient for radio communication, otherwise harmless. Proxima b, even during so-called quiet periods, receives about 0.25 watts per square meter of X-ray radiation. That's 250 times higher than Earth. It still sounds small, a quarter of a watt per square meter. You could barely power an LED with that. But X-rays don't heat, they destroy. At those intensities, sustained over millions of years, they strip atmospheres, they break apart water molecules, they render surfaces sterile. During a flare, the numbers explode. The X-ray flux at Proxima b can spike to 10 watts per square meter or higher, 10,000 times what Earth experiences. That is not a metaphor. That is a direct measurement, extrapolated from observations of the star's flare behavior and the planet's orbital distance. For reference, 10 watts per square meter of X-ray radiation is roughly what you would receive if you stood a few meters away from an industrial X-ray machine running continuously. Except there is no stepping away. The machine is the sky, and it runs for hours at a time, then shuts off for a day or two, then turns back on. The source of all this radiation is Proxima Centauri's magnetic field. Red dwarfs, being fully convective, generate magnetic fields through a dynamo process that operates throughout the entire star. The magnetic energy builds up as the star rotates, and the convective motions twist the field lines into increasingly complex knots. When those knots snap, the stored energy is released as a flare. The reconnection heats plasma to tens of millions of degrees, accelerates particles to near light speed, and produces a burst of radiation across the electromagnetic spectrum. Most of that energy comes out in the X-ray and extreme ultraviolet bands. Those are the wavelengths that do the damage. The energy itself is one problem. The other problem is what that energy does when it hits an atmosphere. Earth's atmosphere is about 78% nitrogen and 21% oxygen, with traces of argon, carbon dioxide, and water vapor. The top of the atmosphere sits about 100 kilometers above the surface. When X-rays from the sun hit that upper layer, they ionize nitrogen and oxygen molecules, stripping electrons and creating a layer of charged particles called the ionosphere. The process is gentle. The sun's X-ray output is low, and the atmosphere is thick enough to absorb the radiation without losing much mass. Over billions of years, Earth has lost almost no atmosphere to X-ray heating. Proxima b, if it ever had an atmosphere, would be in a very different situation. The X-ray flux is 250 times higher. That means 250 times more ionization, 250 times more heating in the upper atmosphere. And heating matters because when gas heats up, it expands. If it expands fast enough, it reaches escape velocity. The atmosphere literally boils away into space. Planetary scientists have a term for this: hydrodynamic escape. It's the process by which a planet loses its atmosphere, not through slow leakage, one molecule at a time, but through a sustained atmospheric wind driven by intense heating. The gas expands upward, accelerates, and streams off into space like steam from a boiling pot. For a planet sitting as close to a flaring red dwarf as Proxima b does, hydrodynamic escape is not a minor effect. It is the dominant atmospheric loss mechanism. Researchers have modeled this process in detail. They start with a hypothetical Proxima b that has an Earth-like atmosphere: 78% nitrogen, 21% oxygen, 1 bar of surface pressure. Then they expose it to the X-ray and ultraviolet environment measured around Proxima Centauri. The models include the star's flares, the baseline X-ray flux, the ultraviolet radiation, and the stellar wind, the stream of charged particles constantly blowing off the star's surface. They run the simulation forward for billions of years and watch what happens. The atmosphere erodes fast. Within the first few 100 million years, the planet loses a significant fraction of its atmospheric mass. The lighter elements, hydrogen and helium, if there were any to start with, escape almost immediately. Water vapor in the upper atmosphere gets photodissociated by ultraviolet light, split into hydrogen and oxygen. The hydrogen escapes. The oxygen either escapes too, or reacts with surface rocks and gets locked away. Over the course of 1 billion years, an ocean's worth of water can be lost this way. By the time the planet is a few billion years old, the atmospheric pressure has dropped below 10% of Earth's. By 4 billion years, the age of the Proxima Centauri system today, the atmosphere is effectively gone. What's left is a thin wisp of gas, surface pressure well under 1 millibar, far too tenuous to support liquid water. The planet is a desiccated rock. This is not speculation. This is the result of running physics forward in time, using the measured properties of the star and reasonable assumptions about the planet. You can tweak the initial conditions. You can start with a thicker atmosphere, or more water, or different atmospheric composition. You can add a magnetic field to try to protect the planet. The result changes in detail, but not in outcome. Proxima b, under the relentless assault of X-rays and ultraviolet radiation from its host star, cannot hold on to a habitable atmosphere over geological time. The magnetic field question is worth pausing on because it's one of the few possible defenses a planet could have. Earth's magnetic field deflects much of the solar wind, channeling charged particles toward the poles where they create auroras instead of stripping away the atmosphere. Without that magnetic field, Earth would be in serious trouble. Mars is the cautionary tale. Mars once had a thicker atmosphere and possibly liquid water on its surface. Then its magnetic field shut off, probably because the planet's core cooled and solidified, and over the next few billion years the solar wind stripped most of the atmosphere into space. Today Mars has surface pressure less than 1% of Earth's, too thin for liquid water, too thin for much of anything. Proxima b, being tidally locked, probably rotates very slowly. Tidal locking happens when a moon or planet's rotation period matches its orbital period, so the same side always faces the star. Earth's moon is tidally locked to Earth. You only ever see one face of the moon from Earth's surface because the moon rotates once every time it completes an orbit. Proxima b almost certainly is tidally locked to Proxima Centauri, because tidal forces are strong at close orbital distances, and the planet has had billions of years to settle into that configuration. Slow rotation is bad news for magnetic field generation. Earth's magnetic field is produced by a dynamo in the outer core, a layer of liquid iron that flows in convective currents driven by heat from the inner core and the planet's rotation. The rotation is key. It organizes the flow into patterns that amplify the magnetic field. A planet that rotates once every 11 days instead of once every 24 hours has a much weaker dynamo. The flow is slower. The magnetic field is weaker, maybe too weak to matter. Some models suggest Proxima b could still have a magnetic field if its core is large enough and still molten. But even a relatively strong field might not be enough. The stellar wind from Proxima Centauri is not like the solar wind. It is denser, faster, and loaded with more energetic particles. The flares add bursts of plasma traveling at significant fractions of the speed of light. A magnetic field that would easily deflect the solar wind might be overwhelmed by the Proxima wind, and even if the field holds, even if it deflects most of the charged particles, the X-rays still get through. Magnetic fields do not deflect light, they deflect charged particles. X-rays, being photons, travel right through the magnetosphere and into the atmosphere where they ionize gas and drive hydrodynamic escape. The habitable zone, as a concept, was never designed to account for this. It was designed to identify where planets could be warm enough for liquid water. It treats stars as point sources of energy and planets as passive absorbers. It ignores stellar activity. It ignores atmospheric composition. It ignores magnetic fields and radiation chemistry and all the messy details that determine whether a planet is actually habitable versus just being in the right temperature range. For Sun-like stars, that simplification works reasonably well. The Sun is stable. Its X-ray and ultraviolet output is low. Planets in the habitable zone are, broadly speaking, decent candidates for life. For red dwarfs, the simplification breaks down completely. Proxima b is the poster child for this breakdown. By the traditional definition, it is in the habitable zone. By any realistic assessment that includes the actual radiation environment, it is a hellscape. The planet is not habitable. It is bombarded. The surface, if you could somehow stand on it, would be bathed in ultraviolet and X-ray radiation at levels that would give you a lethal dose in minutes. There is no ozone layer to block the UV. There is probably no atmosphere at all. The ground beneath your feet would be scorched rock, chemically altered by billions of years of radiation exposure. The sky above you, if the day side of the planet is facing the star, would not be blue. It would be a dim red glow, the color of Proxima Centauri's infrared output. And every day or two, that glow would explode into a blinding flare that would flood the surface with enough X-rays to sterilize anything that had somehow survived the last flare. There is no water. Any oceans the planet might have started with boiled away eons ago. The hydrogen escaped into space. The oxygen either followed or got locked into surface minerals, oxidizing iron in the crust and leaving rust-colored deserts. If there are any volatiles left, they are frozen on the night side, the hemisphere permanently facing away from the star, where temperatures drop to 100 degrees Kelvin or colder. Water ice, carbon dioxide ice, maybe nitrogen ice if any nitrogen survived the atmospheric erosion. But that ice is not accessible, it is not melting, it is not part of any active hydrological cycle. It is just sitting there, locked in eternal darkness, while the day side roasts under the unblinking red eye of Proxima Centauri. Astrobiologists have tried to salvage the situation. Maybe, some have suggested, life could survive underground. If there are caves or subsurface aquifers or pockets of liquid water deep enough to be shielded from the radiation, maybe something could cling to existence there. It is not impossible. Earth has deep subsurface biospheres. Bacteria live kilometers underground, cut off from sunlight, deriving energy from chemical reactions between water and rock. If Proxima b has geothermal heat, if it has liquid water at depth, if it has the right minerals, then in principle life could exist there. But that is a lot of ifs, and it is a far cry from the vision of a habitable world that the initial discovery inspired. The planet is not a second Earth. It is not a place you could terraform. It is not a place where forests could grow or oceans could teem with life. It is, at best, a place where extremophiles might eke out a miserable existence in lightless cracks beneath a dead surface. That is not what anyone means when they talk about habitability. The worst part is that Proxima b is not unique. Red dwarfs are the most common type of star in the galaxy. About 70% of all stars are red dwarfs, and many of them are flare stars like Proxima Centauri. If the nearest red dwarf behaves this way, if its planets are subjected to this kind of punishment, then it is reasonable to assume that many other red dwarf systems are similar. The habitable zones around those stars might be full of planets, and those planets might all be uninhabitable. This has profound implications for the search for life in the universe. For years, red dwarfs were considered promising targets. They are abundant. They are long-lived. They burn their fuel slowly, giving planets billions or even trillions of years to develop life, and their habitable zones are close in, which makes planets easier to detect using current methods. But if the habitable zones around red dwarfs are radiation traps, then the number of truly habitable worlds in the galaxy just dropped by a factor of 2 or 3, maybe more. There are astronomers who push back against this pessimism. Maybe, they argue, some red dwarfs are quieter than Proxima Centauri. Maybe some planets are better shielded. Maybe life is more resilient than we think. Maybe our models are too conservative. These are fair points. Science is not about certainty. It is about probabilities and evidence, and constantly updating your understanding as new data comes in. But the data we have right now, from Proxima Centauri specifically, does not leave much room for optimism. The 250 times Earth X-ray flux number is not an estimate, it is a measurement. Astronomers have observed Proxima Centauri across multiple wavelengths, during flares and between flares, for years. They have calculated the energy output in X-rays and ultraviolet light. They have measured the frequency and intensity of the flares. They have plugged those numbers into atmospheric models. The models do not predict a happy ending. They predict atmospheric loss. They predict surface sterilization. They predict a planet that looks nothing like the habitable world we hoped to find. The concept of the habitable zone is not wrong, it is incomplete. It was always incomplete, but for decades we did not have the data to see the gaps. Proxima b showed us the gaps. It showed us that being in the habitable zone is necessary but not sufficient. A planet needs more than the right temperature. It needs a stable star. It needs a protective magnetic field. It needs a thick enough atmosphere to withstand erosion. It needs a radiation environment that does not constantly undo whatever chemistry is trying to happen on the surface. Proxima b has the right temperature range. It has almost nothing else. When the discovery was announced in 2016, there were serious proposals to send a probe. The Breakthrough Starshot initiative, backed by Stephen Hawking and funded by Yuri Milner, had already been working on the concept of laser-propelled light sails that could reach Alpha Centauri within a human lifetime. Adding Proxima Centauri to the target list made perfect sense. Send a tiny probe, accelerate it to 20% the speed of light, and let it coast for 20 years until it reaches the Proxima system. Take pictures, measure the planet, confirm whether it has an atmosphere, maybe even look for biosignatures, chemical traces that could indicate life. That dream has not died, but it has dimmed. The more we learn about Proxima Centauri, the less appealing the destination looks. A probe could still tell us valuable things. It could measure the planet's magnetic field. It could analyze the surface composition. It could confirm whether the atmosphere is gone or just very thin. But the hope of finding life there, or even finding conditions where life could have existed in the recent past, has all but evaporated. The star has seen to that. Proxima b is still the closest known exoplanet. It is still sitting in the habitable zone by the traditional definition, and it is still, almost certainly, a barren, irradiated rock. The habitable zone did not lie, it just did not tell the whole truth, and the truth, as it turns out, is written in X-rays, 250 times brighter than anything Earth has ever faced, relentless, inescapable. The sky itself, on Proxima b, is hostile, not in a poetic sense, in a measurable, physical, lethal sense. The planet orbits through a radiation field that would kill anything we recognize as life within hours, and it has been doing that for 4.5 billion years. Whatever Proxima b was when it formed, whatever water it had, whatever atmosphere it started with, the star has taken it all away. What remains is a cautionary tale, a reminder that proximity is not hospitality, and a planet in the habitable zone is not necessarily a planet where anything could live. Sometimes it is just a world bathed in X-rays and despair, and sometimes the universe does not hand you a gift, it hands you a lesson. Proxima b is that lesson, written in radiation, delivered across 4.24 light-years, arriving now, clear as daylight, harsh as truth. The planet has two faces, and neither one of them is welcoming. This is not a metaphor, this is not poetic language. Proxima b, sitting just 7.3 million kilometers from its host star, has been locked in place by gravity. One hemisphere faces Proxima Centauri permanently, basking under an unblinking red sun that never sets. The other hemisphere faces away into the eternal dark, frozen in a night that has lasted for billions of years and will continue until the star itself dies. There is no sunrise on Proxima b, there is no sunset, there is no day-night cycle, no rotation to speak of, no spin that would give the planet's surface any relief from the extremes it endures. The world is divided, one side burns, the other freezes, and the narrow band between them, the terminator line where day meets night, is the only place on the entire planet where conditions might be anything close to stable. This is tidal locking, and it is one of the most consequential physical conditions a planet can have. The process that leads to tidal locking is well understood. When a planet orbits close to its star, the star's gravity pulls harder on the side of the planet facing it than on the side facing away. That difference in gravitational pull, called a tidal force, creates a bulge. The planet deforms slightly, stretched into an egg shape, with the long axis pointing toward the star. If the planet is rotating, that bulge tries to stay aligned with the star, but the rotation drags it out of alignment. The star's gravity then pulls on the misaligned bulge, creating a torque that slows the planet's rotation. Over millions of years, the rotation slows and slows until it matches the orbital period exactly. At that point, the same side of the planet always faces the star. The bulge stays put. The torque drops to zero. The planet is tidally locked. Our own moon is tidally locked to Earth. You have seen this your entire life without necessarily thinking about it. The face of the moon you see from Earth is always the same. The far side of the moon, the side that never faces Earth, was a complete mystery until spacecraft flew around it and took pictures. The moon rotates once every 27.3 days, which is exactly how long it takes to orbit Earth once. One face toward us, always. One face away, always. The process that locked the moon to Earth is the same process that locked Proxima b to its star. Tidal locking happens faster when the planet is close to the star and when the star is massive relative to the planet. Proxima b orbits at less than 5% of the distance between Earth and the Sun. The tidal forces at that range are enormous. The planet's rotation would have been slowed to a crawl within the first few 100 million years of its existence. By now, after more than 4 billion years, it is locked tight. The odds that Proxima b is not tidally locked are vanishingly small. Every model, every simulation, every back-of-the-envelope calculation done by every astronomer who has looked at this system says the same thing. The planet does not spin, or rather, it spins exactly once per orbit. Same thing. This is common for planets around red dwarfs. The habitable zones around red dwarfs sit so close to the star that tidal locking is nearly inevitable. If you find a planet in the habitable zone of a red dwarf, you can assume with high confidence that it is tidally locked unless something very unusual is going on. It is not a quirk of Proxima b, it is the default condition for planets like it, and that has implications that ripple through every aspect of the planet's environment. Start with temperature. The day side of Proxima b, the hemisphere that faces the star, is hot. Not Venus hot, not Mercury hot, but hot enough. Estimates vary depending on how much atmosphere the planet has and how reflective its surface is, but the numbers cluster around 100 to 400 degrees Celsius at the subsolar point, the spot on the surface directly beneath the star where the sun sits motionless at the zenith. 400 degrees Celsius is well above the boiling point of water. Even at 100 degrees, liquid water cannot exist without significant atmospheric pressure to keep it from boiling away. And if Proxima b has lost most of its atmosphere to stellar wind and radiation, which the models suggest it has, then atmospheric pressure is not going to save anything. The night side is the opposite problem. With no sunlight ever reaching it, the temperature drops. How far it drops depends on whether the planet has an atmosphere thick enough to transport heat from the day side to the night side. If there is no atmosphere, or only a very thin one, then the night side would radiate heat into space until it reached equilibrium with the cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space. That temperature is about 2.7 Kelvin, or roughly minus 270 degrees Celsius. Nothing lives at minus 270 degrees, nothing moves. Atoms barely vibrate. More realistically, if Proxima b has any atmosphere at all, even a thin one, it would transport some heat from the hot side to the cold side through atmospheric circulation. Winds would blow from day to night, carrying thermal energy. The night side would not cool all the way to cosmic microwave background temperatures. It would settle somewhere warmer, still cold but not absolute zero cold. Estimates for the night side temperature range from -100 degrees Celsius to -10 degrees, depending on how thick the atmosphere is and how efficient the heat transport is. At the cold end of that range, carbon dioxide would freeze out of the atmosphere and fall as dry ice snow, piling up in glaciers on the night side. At the warm end, you might have liquid water in the form of subsurface ice melting into briny pools, but the surface would still be frozen, and the sky would still be black, and the star would never rise. The gradient between the two hemispheres is staggering. 400 degrees on one side, -100 on the other. A temperature difference of 500 degrees across a single planet. For comparison, the temperature difference between Earth's equator and its poles is roughly 100 degrees Celsius, and that difference drives hurricanes, jet streams, ocean currents, and most of the weather patterns we experience. Proxima b has 5 times that gradient, and it does not have the moderating influence of a day-night cycle to smooth things out. The hot side stays hot, the cold side stays cold. The only place where conditions might be moderate is the thin strip of land running around the planet along the terminator, the line dividing day from night. Astronomers have taken to calling tidally locked planets with this kind of extreme temperature gradient eyeball planets. The name comes from the way they might look if you could see them from space. The day side would be bright, possibly covered in bare rock or reflective clouds. The night side would be dark, possibly covered in ice. And in between, along the terminator, there might be a ring of liquid water, a narrow band where temperatures hover near 0 degrees Celsius and ice can melt. From a distance, the planet would look like a giant eyeball, with the day side as the white of the eye, the night side as the surrounding darkness, and the terminator as the iris and pupil. It is a vivid image. It is also speculative. No one has ever directly observed the surface of an exoplanet. The eyeball planet is a model, a prediction based on simulations of atmospheric circulation and energy balance, but the model has been run dozens of times by different research groups, and it keeps producing the same basic result. If Proxima b has a thin atmosphere and any surface water left, that water will be concentrated in a narrow habitable ring. The width of that ring depends on the details. If the atmosphere is thick, it can transport heat efficiently, and the habitable zone might extend further onto the day side and night side. If the atmosphere is thin, the ring shrinks. In the most optimistic models, the habitable zone could cover as much as 20% of the planet's surface. In the pessimistic models, it shrinks to a band a few hundred kilometers wide running along the equator. Either way, it is not a lot of real estate. The vast majority of the planet would be uninhabitable, too hot or too cold. The terminator is the only refuge, and even the terminator is not exactly welcoming. The temperature might be moderate, hovering somewhere between 0 and 25 degrees Celsius, the range where liquid water is stable. But the sun never moves. It sits on the horizon forever. The sky would be a perpetual twilight, the star half visible, casting long shadows that never shift. There would be no circadian rhythm, no seasons, no variation in sunlight, just a constant dim red glow from the direction of the day side, fading into darkness as you walk toward the night side. If you were standing on the terminator, you could walk toward the day side and watch the sun slowly climb higher in the sky until the heat became unbearable. Or you could walk toward the night side and watch the sun sink below the horizon until the cold forced you to turn back. The Terminator is not a place, it is a boundary, a narrow margin between two extremes. The atmospheric dynamics on a tidally locked planet are nothing like Earth's. On Earth, the sun moves across the sky, heating different parts of the surface at different times of day. That uneven heating drives convection. Warm air rises, cool air sinks, and the rotation of the planet organizes that convection into large-scale patterns like the Hadley cells, the mid-latitude jet streams, and the polar vortices. Weather on Earth is complicated, but it follows predictable patterns shaped by the day-night cycle and the planet's rotation. Proxima b has none of that. The sun does not move. The heating is constant on the day side and absent on the night side. The result is a single massive convection cell stretching from the subsolar point to the antisolar point, the spot on the night side directly opposite the star. Hot air rises at the subsolar point, flows outward toward the edges of the day side, then sinks and flows back toward the night side along the surface. From the night side, cold, dense air flows back toward the day side at low altitude, completing the loop. This is not a weather pattern, it is a planetary scale conveyor belt. The winds driven by this convection are extreme. The pressure gradient between the hot day side and the cold night side is enormous, and air flows from high pressure to low pressure, fast. Simulations suggest wind speeds on Proxima b could reach 100 meters per second or more, roughly 220 miles per hour, sustained indefinitely. For reference, a Category 5 hurricane on Earth has sustained winds of at least 70 meters per second. The entire surface of Proxima b, particularly along the Terminator where the wind is strongest, would be scoured by hurricane-force winds that never stop. No calm days, no light breezes, just a constant howling gale, day after day, year after year, eon after eon. Those winds would carry dust and debris from the day side to the night side, depositing material in massive drifts along the night side equator. Over geological time, the surface would be reshaped by wind erosion on a scale Earth has never seen. The Terminator, the only potentially habitable zone, would be a wind tunnel. Any structure, any landform, any organism trying to survive there would have to contend with relentless mechanical stress. Plants, if they existed, could not grow tall. They would be flattened. Animals, if they existed, would need to burrow or seek shelter in valleys and canyons where the wind was blocked. The surface would be a sand-blasted wasteland. The winds also transport heat. That is the only reason the night side does not freeze to absolute zero. Air heated on the day side flows toward the night side, carrying thermal energy with it. By the time it reaches the night side, it has cooled somewhat, but it is still warmer than the local environment. That warmth keeps the night side from becoming completely uninhabitable. But the process is not efficient. Most of the heat is radiated back into space before it reaches the deep night side. The result is a steep temperature gradient across the Terminator. A few hundred kilometers can mean the difference between above freezing and well below freezing. Walking from the temperate zone into the night side would be like walking from a spring day into the Arctic winter, except you would only need to walk for an hour or two to make the transition. Water, if there is any on Proxima b, would follow the winds. Water vapor evaporated from the hot day side would be carried by the atmospheric circulation toward the night side. As the air cooled, the water vapor would condense into clouds, then rain, then snow, and finally freeze solid. Over millions of years, this process would transport water from the day side to the night side, where it would be locked up as ice. The night side would accumulate massive glaciers, kilometers thick, covering continents. The day side would dry out, becoming a desert. This is called atmospheric collapse, and it is one of the major concerns for habitability on tidally locked planets. If all the water ends up frozen on the night side, there is none left for life on the day side or the terminator. The only way to prevent atmospheric collapse is to have a thick enough atmosphere that the pressure keeps water from freezing even on the night side, or to have enough geothermal heat from the planet's interior to melt ice at the base of the night side glaciers, creating subsurface oceans that feed back into the atmospheric cycle. Both of these require specific conditions that may or may not exist on Proxima b. We do not know. We cannot observe the planet's surface directly. The planet is too close to its star and too far from Earth for current telescopes to resolve any detail. Everything we think we know about the surface conditions is based on models, and models are only as good as the assumptions you feed into them. One of the key uncertainties is how much atmosphere Proxima b has. If the planet started with an Earth-like atmosphere and has been battered by stellar flares for 4 billion years, it might have lost most of it by now. A thin atmosphere cannot transport heat efficiently. The day side would roast, the night side would freeze, and the terminator would be a razor-thin band where conditions are barely tolerable. On the other hand, if the planet somehow retained a thick atmosphere, or if volcanic outgassing has been replenishing the atmosphere over geological time, then heat transport would be more efficient, the habitable zone would be wider, the night side might not freeze completely. Life, if it exists, would have more room to work with. Another uncertainty is the surface composition. If the day side is covered in reflective materials, like ice or light-colored rock, it would reflect more sunlight back into space and stay cooler. If the surface is dark, like basalt or carbon-rich compounds, it would absorb more heat and get hotter. The same applies to the night side. A dark surface radiates heat more efficiently than a light surface. These details matter. They can shift the temperature on the day side by tens of degrees, which in turn shifts the width of the habitable terminator zone. There is also the question of topography. Mountains, valleys, and ocean basins all affect local climate. A deep valley on the terminator might trap warm air and provide a stable microclimate, even if the surrounding highlands are too cold. A mountain range could block the wind, creating a sheltered zone where conditions are less extreme. On Earth, topography plays a huge role in determining where life can thrive. The same would be true on Proxima b, only more so because the environmental gradients are so steep. The possibility of a twilight zone, a habitable band along the terminator, has captured the imagination of astrobiologists. If life exists on Proxima b, that is where it would be. Not on the scorched day side, not on the frozen night side, in the narrow strip where the sun hangs low on the horizon and temperatures stay within the range where liquid water can exist. The environment would be harsh. Constant wind, dim red light, no day-night cycle, extreme radiation during flares. But life on Earth thrives in harsh environments too. Bacteria live in boiling hot springs, in acidic lakes, in the freezing deserts of Antarctica, in the lightless depths of the ocean. If life is possible on Proxima b, it would have to be something like those extremophiles. Hardy, resilient, adaptable, not lush forests or teeming oceans, microbial mats clinging to rocks, chemosynthetic organisms drawing energy from minerals rather than sunlight. Life at the margins. The irony is that the terminator, the only potentially habitable zone, is also the most geologically unstable part of the planet. The constant wind erosion, the thermal stress from the temperature gradient, and the mechanical stress from tidal forces all concentrate along the terminator. The surface would be fractured, unstable, prone to landslides and collapse. not exactly prime real estate. And there is one more problem. Even if the Terminator has liquid water and moderate temperatures, it is still in the line of fire. Every time Proxima Centauri erupts in a superflare, the Terminator gets hit with the same dose of X-rays and ultraviolet radiation as the rest of the planet. There is no hiding from that. The atmosphere, if there is one, might absorb some of the radiation before it reaches the surface. But if the atmosphere is thin, and if the flares are frequent and intense, then even the Terminator is a radiation hazard. Life would need to shelter underground, in caves or beneath layers of rock, emerging only during the rare quiet periods between flares. It is not impossible, but it is not easy. The models have been run by multiple research groups over the years. In 2016, shortly after the discovery of Proxima b, a team at NASA Goddard, led by Anthony Del Genio, published simulations of the planet's climate, assuming it had an Earth-like atmosphere. Their conclusion was cautiously optimistic. There is a decent chance of a liquid water band around the Terminator, they said, though the exact width and stability of that band depend on details we cannot yet measure. The planet is not automatically uninhabitable just because it is tidally locked. But it is not automatically habitable either. A year later, a team at the European Space Agency led by Stamatios Laskaridis published a more pessimistic assessment. They argued that the stellar wind from Proxima Centauri is strong enough to strip away any atmosphere over geological time, especially during the frequent flares. Without an atmosphere, there is no heat transport. The planet becomes a two-faced desert, one side molten, one side frozen, with no habitable zone at all. Their models suggested that even if Proxima b started with a thick atmosphere, it would be gone by now. The Terminator would be a barren wasteland. The truth, as usual, is probably somewhere in between. Proxima b might have some atmosphere left, but not as much as Earth. The Terminator might have liquid water, but only in isolated pockets. The wind might be extreme, but not quite as bad as the worst-case models predict. Life might exist, but only in the most sheltered, radiation-protected niches. None of this can be confirmed without direct observation. And direct observation, for a planet this close to its star and this far from Earth, is still beyond our current capabilities. What we do know for certain is that tidal locking fundamentally changes the game. It removes one of the most basic features of a habitable planet, the day-night cycle, and replaces it with a static two-hemisphere system where extremes dominate. Earth's habitability depends on its rotation. The spin spreads the sun's energy evenly over the surface. It drives atmospheric circulation, ocean currents, and seasonal cycles. It gives life a rhythm, a predictable pattern of light and dark, warm and cold that organisms can adapt to. Proxima b has none of that. The rhythm is broken. The pattern is gone. What remains is a planet frozen in time, one face toward the star, one face away, and a narrow band in between where conditions might, just barely, be tolerable. The question is whether tolerable is enough. Can life take hold in a place where the sun never moves, where the wind never stops, where radiation spikes without warning, and where the only liquid water exists in a band a few hundred kilometers wide? On Earth, life adapts to almost anything, but Earth also benefits from a stable star, a protective magnetic field, a thick atmosphere, and a day-night cycle that distributes energy evenly. Proxima b has none of those advantages. It is not impossible that life could exist there, but it is vanishingly unlikely that it could thrive. Tidal locking is not unique to Proxima b. It is the default state for planets in the habitable zones of red dwarfs, and red dwarfs are the most common stars in the galaxy, which means that if tidal locking makes planets uninhabitable, or even just drastically reduces their habitability, then the number of potentially habitable worlds in the universe just dropped by a huge margin. For years, astronomers hoped that red dwarf systems would be havens for life because the stars are so abundant and so long-lived. Proxima b is teaching us that abundance does not guarantee hospitality. It is teaching us that a planet can sit in the habitable zone at the right distance with the right temperature range and still be utterly hostile to life, not because the planet itself is broken, but because the star and the orbital dynamics and the radiation environment and the tidal forces all conspire to create conditions that are just barely on the wrong side of survivable. The two faces of Proxima b tell the same story from opposite angles. The day side says, too much, too hot, too bright, too exposed. The night side says, too little, too cold, too dark, too isolated. And the Terminator, the thin line between them, says, maybe, if you are lucky, if the conditions are just right, if the atmosphere holds, if the water does not freeze, if the flares do not kill you. Maybe. That is not the answer anyone wanted when Proxima b was discovered, but it is the answer the data keeps giving. And as we turn our attention to red dwarfs as a class, to the billions of stars like Proxima Centauri scattered throughout the galaxy, we start to see the same pattern repeated. These stars are not gentle. Their habitable zones are not refuges. They are testing grounds, places where the universe asks, how resilient is life? How adaptable? How desperate? And whether anything on Proxima b has managed to answer that question, we do not yet know. Proxima Centauri is not special. That needs to be said up front because everything about the discovery of Proxima b, everything about the excitement and the subsequent disappointment, carries an unspoken assumption that this star is unique, a cosmic outlier, an unusually violent neighbor in an otherwise calm stellar neighborhood. It is not. Proxima Centauri is a red dwarf. And red dwarfs, for all their dimness, for all their obscurity in the night sky, are the rulers of the galaxy, not metaphorically, literally. By sheer weight of numbers, by longevity, by their total claim on the stellar real estate of the Milky Way, red dwarfs dominate. They are the most common type of star in existence. And almost everything we have learnt about Proxima Centauri applies to billions of other stars scattered throughout the galaxy. Billions. The violence is not the exception, it is the rule. Red dwarfs make up roughly 70% of all stars in the Milky Way. 70%. That is not a guess. That is a census figure, derived from decades of surveys combining ground-based telescopes, space observatories, and statistical models that extrapolate from the stars we can see to the ones too dim to detect directly. For every bright star you can see with your naked eye on a clear night, every Sirius and Vega and Betelgeuse, there are hundreds of red dwarfs invisible to you, too faint to register without a telescope. The galaxy is full of them, packed with them. They outnumber sun-like stars by a ratio of roughly 9-to-1. They outnumber the massive blue giants and supergiants by factors of thousands. If you picked a star at random from the Milky Way, 7 times out of 10 it would be a red dwarf. This dominance was not obvious for a long time. When early astronomers catalogued the stars, they naturally noticed the bright ones first, the ones that stood out, the ones that anchored constellations and served as navigation markers. Red dwarfs did not make the cut. They were too dim. Even the nearest red dwarf, Proxima Centauri, sitting just over 4 light-years away, was not discovered until 1915 because it required photographic plates and careful comparison to even notice its existence. Before photography, red dwarfs were effectively invisible. Astronomers spent centuries mapping the heavens without realizing they were missing most of the stars. The term red dwarf itself is descriptive. Red because they are cool and emit most of their light in the red and infrared portions of the spectrum. Dwarf because they are small. A typical red dwarf has a mass somewhere between 8% and 50% of the Sun's mass. Anything below 8% cannot sustain hydrogen fusion in its core and becomes a brown dwarf instead, a failed star that glows faintly from leftover heat. Anything above 50% transitions into the orange dwarf category, slightly hotter and brighter. The red dwarf range is narrow in terms of mass but enormous in terms of population. Size-wise, red dwarfs are tiny. Their radii range from about 10% to 20% of the Sun's radius. The smallest ones are barely larger than Jupiter, the largest planet in our solar system. Jupiter is not a star. It does not fuse hydrogen, but it is roughly the same size as many red dwarfs, which gives you a sense of scale. If you placed a red dwarf next to the Sun would look like a giant. If you placed a red dwarf next to a blue supergiant like Rigel, the red dwarf would be a speck. The surface temperature of a red dwarf ranges from about 2500 to 4000 Kelvin. For comparison, the Sun's surface temperature is roughly 5700 Kelvin. Cooler surfaces mean less energetic photons. Most of the light coming from a red dwarf is in the infrared, which human eyes cannot see. If you could somehow visit a planet orbiting a red dwarf and look up at the star, you would not see a white or yellow sun like ours. You would see a dim red or orange glow, like a dying ember, faint enough that the landscape around you might feel more like twilight than daylight even at noon. Despite their small size, red dwarfs are incredibly dense. The same mass that would be spread out over a much larger volume in a sun-like star is compressed into a smaller space. That compression has consequences. The core of a red dwarf is hot enough and dense enough to sustain hydrogen fusion, the process that powers all main sequence stars. But because the star is so small, the core is a much larger fraction of the total volume. In a sun-like star, the core occupies maybe the inner 25% of the radius. In a red dwarf, the core can extend out to 50% or more. That changes the internal structure. In sun-like stars, energy generated in the core moves outward through two distinct zones. The inner radiative zone, where energy travels via photons bouncing from atom to atom in a slow random walk, and the outer convective zone, where energy moves via bulk motion of hot plasma rising to the surface and cool plasma sinking back down. The boundary between these two zones is where the Sun's magnetic dynamo operates, the mechanism that generates the magnetic field responsible for sunspots and solar flares. Red dwarfs do not have that boundary. They are fully convective. The entire star, from core to surface, churns like a pot of boiling water. There is no radiative zone. Energy moves via convection throughout the entire volume. That means the magnetic dynamo is not confined to a narrow shell. It operates everywhere at once. The result is a magnetic field structure far more complex and far more unstable than what you find in a sun-like star. Magnetic field lines twist and tangle throughout the entire star, building up energy until they snap in violent reconnection events that we observe as flares. This is why so many red dwarfs are flare stars. Proxima Centauri is classified as a flare star, indicated by the lowercase e in its spectral type M5.5VE. The E stands for emission lines in the spectrum, a sign that the star has an active chromosphere and is prone to eruptions. But Proxima is not unusual in this regard. Most red dwarfs, especially the smaller and cooler ones, are flare stars. The fully convective structure almost guarantees it. The magnetic fields are too tangled, the energy buildup too constant. Flares are the release valve. The other defining characteristic of red dwarfs is their lifespan. Stars live by burning hydrogen into helium in their cores. The more massive a star is, the hotter its core, and the faster it burns through its fuel. Massive stars, the blue giants and supergiants, burn so hot and so fast that they exhaust their hydrogen in just a few million years before exploding as supernovae. Sun-like stars burn more slowly. Our Sun has been on the main sequence for about 4.6 billion years and has roughly another 5 billion years to go before it runs out of hydrogen and begins its transformation into a red giant. Red dwarfs burn their fuel almost incomprehensibly slowly. A red dwarf with Proxima Centauri's mass, about 12% of the Sun's mass, will remain on the main sequence for roughly 4 trillion years. 4 trillion. The universe itself is only about 13.8 billion years old. The Sun will be dead for trillions of years before Proxima Centauri runs out of hydrogen. The smallest red dwarfs, those with masses just above the brown dwarf threshold, could last for 10 trillion years or more. There are red dwarfs alive today that will still be burning when the universe is 100 times older than it is now. This longevity has profound implications. When astrobiologists think about where life might arise, one of the factors they consider is time. Life on Earth took hundreds of millions of years to develop, from simple chemistry to single-celled organisms, and billions of years to progress from single cells to complex multicellular life. If you want a planet to develop life, you need a star that will stick around long enough for that process to unfold. Sun-like stars give you 10 billion years, which is plenty. Red dwarfs give you trillions. If time is what life needs, red dwarfs have it in abundance. The problem is that time alone is not enough. You also need stable conditions. A planet cannot develop life if it is being sterilized every other day by superflares, and that is where the red dwarf story gets complicated. For years, astronomers saw red dwarfs as prime candidates for hosting habitable planets. They are abundant, they are long-lived. Their habitable zones are close in, which makes planets easier to detect and easier to study. The logic seemed airtight. If life is out there, red dwarf systems should be full of it. Then we started looking closely at red dwarf systems, and the logic fell apart. Proxima Centauri is a textbook example, but it is not alone. Astronomers have been cataloging flare activity from red dwarfs for decades. The more they look, the more flares they find. In 2018, NASA's Transiting Exoplanet Survey satellite, TESS, observed a red dwarf called Wolf 359. The star erupted in a superflare that increased its brightness by a factor of 5 in less than 5 minutes. The flare released energy equivalent to about 10% of the Sun's total annual output. And Wolf 359 is not a particularly extreme red dwarf. It is just a typical M dwarf doing what M dwarfs do. Another example is AD Leonis, a red dwarf about 16 light-years from Earth. In 1960, astronomers observed a flare from AD Leonis that increased its brightness by nearly a factor of 10. Follow-up observations over the years confirmed that AD Leonis erupts frequently, sometimes multiple times per day. The flares are large enough to be detected by ground-based telescopes, and the X-ray output during these events spikes to levels that would be catastrophic for any planets orbiting nearby. Then there is EV Lacertae, a red dwarf about 16.5 light-years away. In April 2008, NASA's SWIFT satellite detected a superflare from EV Lacertae that was thousands of times more powerful than the largest solar flare ever recorded. The flare released roughly 10 to the 33 ergs of energy in a matter of minutes. The star's X-ray output during the flare was equivalent to what the entire sun emits across all wavelengths in an entire day. And this was not a once-in-a-lifetime event. EV Lacerte flares regularly. It is one of the most active flare stars known. These are not cherry-picked examples, they are representative. Surveys of red dwarfs consistently show that flares are common, especially among the smaller and cooler stars. A study published in 2014 by Adam Kowalski and colleagues analyzed flare activity in a sample of red dwarfs observed by the Kepler Space Telescope. They found that flares were detected in a significant fraction of the stars, with the flare rate increasing as the stars got cooler and smaller. The coolest red dwarfs, those with masses around 10 to 20% of the Sun, flared almost continuously. Larger, hotter red dwarfs flared less often, but still far more frequently than Sun-like stars. The picture that emerges is clear. Red dwarfs are not calm, they are volatile. Their small size and fully convective structure create magnetic fields that are constantly tangled and stressed. The fields snap, releasing energy in flares that dwarf anything the Sun produces. And because red dwarfs are so dim in visible light, their flares represent a much larger fraction of their total output. A flare that increases a red dwarf's brightness by a factor of 10 is proportionally more significant than a solar flare that increases the Sun's brightness by a fraction of a percent. For planets orbiting in the habitable zones of red dwarfs, this is a disaster. The habitable zone around a red dwarf sits close to the star, typically within 10 million kilometers or less. For comparison, Mercury orbits the Sun at about 58 million kilometers. Planets in red dwarf habitable zones are hugging their stars tightly, trying to stay warm enough for liquid water to exist. But at that distance, they are sitting ducks for the flares. The radiation hits them full force. The X-rays and ultraviolet light slam into the atmosphere, ionizing gas, heating the upper layers and driving atmospheric escape. Over time, the atmosphere erodes, water is lost, the surface becomes barren. This is not speculation. Planetary scientists have modeled this process for multiple red dwarf systems, and the results are consistent. Planets in the habitable zones of active red dwarfs lose their atmospheres over timescales of hundreds of millions to a few billion years. If the planet starts with an Earth-like atmosphere and no unusually strong magnetic field, the atmosphere is stripped. If the planet has water, the water is photo-dissociated and lost to space. What remains is a desiccated rock, too close to a violent star to ever recover. There are potential exceptions. If a planet has a very thick atmosphere to start with, far thicker than Earth's, it might retain enough gas to stay habitable even after billions of years of erosion. If the planet has a very strong magnetic field, much stronger than Earth's, it might deflect enough of the stellar wind and charged particles to avoid catastrophic loss. If the red dwarf is older and less active, having burned through its magnetic fury in its youth, its planets might have a better shot. These ifs pile up quickly, and each one narrows the range of conditions under which habitability is possible. The irony is almost painful. Red dwarfs are the most common stars in the galaxy. They are the longest-lived stars in the galaxy. They have had more time than any other type of star to develop planets, to nurture chemistry, to give life a chance, and yet their habitable zones are some of the most hostile environments in the cosmos. The universe's most abundant real estate is largely uninhabitable, not because the stars are too hot or too cold or too far apart, but because they are too violent. This has huge implications for the search for life beyond Earth. For decades, the strategy has been to look for Earth-like planets in the habitable zones of Sun-like stars. That makes sense. Earth is our only example of a planet with life, and the Sun is the only star we know can host such a planet. But Sun-like stars are rare. They make up only about 7% of the galaxy. If you restrict your search to Sun-like stars, you are ignoring 93% of the stellar population. Red dwarfs, by contrast, are everywhere. If you could prove that red dwarf habitable zones were safe, the number of potential targets for the search for life would explode. But the data we have suggests the opposite. Red dwarf habitable zones are not safe. They are radiation zones. Some researchers have pushed back. Maybe, they argue, life on red dwarf planets would adapt. Maybe it would evolve thick protective shells, or live underground, or develop biochemistry that is more resistant to radiation. Life on Earth is remarkably resilient. Bacteria thrive in nuclear reactors. Archaea live in boiling acid. Tardigrades can survive the vacuum of space. Why not life that can handle a few superflares? The counter-argument is frequency. A tardigrade can survive a brief exposure to extreme conditions. It cannot survive constant bombardment, and red dwarf flares are not rare events. They are routine. The radiation environment is not occasionally hostile. It is persistently hostile. That is a much higher bar for life to clear. There is also the question of tidal locking. Planets in red dwarf habitable zones are almost certainly tidally locked, with one side permanently facing the star. That creates its own set of problems, from extreme temperature gradients to potential atmospheric collapse. Even if a planet can retain an atmosphere despite the flares, the tidal locking might make habitability impossible for other reasons. The combination of flares, radiation, and tidal locking stacks the deck heavily against life. And yet red dwarfs are not going anywhere. They will be here long after sun-like stars have burned out. In a few billion years, the Sun will enter its red giant phase, swelling up to engulf the inner planets before shedding its outer layers and collapsing into a white dwarf. Red dwarfs will still be on the main sequence, burning steadily, unchanged. In 1 trillion years, when the universe is cold and dark and most of the star formation has ceased, red dwarfs will still be shining. They are the future of the galaxy, the last lights that will go out. And if their habitable zones are uninhabitable, then the long-term future of the galaxy is a lonely one. There is one more angle to consider. Red dwarfs might not be the best places for life to start, but they could be the best places for life to end up. If a civilization arose around a sun-like star and developed the technology to travel between stars, red dwarfs would be attractive destinations. They are abundant, they are nearby, and they will outlast every other type of star. A sufficiently advanced civilization would not need a planet in the habitable zone. They could build habitats in orbit, shielded from radiation, harvesting energy from the star, and living in space. The flares would be an engineering challenge, not an existential threat. In that scenario, red dwarfs are not hostile. They are resources, fuel for a civilization that has learned to survive without planets. But that is speculative. What is not speculative is the data. The data says that red dwarfs are common, long-lived, and violent. The data says that Proxima Centauri is not an outlier, it is typical. The data says that 70% of the stars in the galaxy are red dwarfs, and most of them behave like Proxima, flaring, erupting, bathing their planets in radiation. The habitable zones are there, drawn neatly on charts and diagrams, but they are habitable in name only. The math that defines them accounts for temperature. It does not account for violence. This realization has been slow to sink in. For years, the excitement around red dwarf exoplanets was high. Every new discovery, every planet in the habitable zone of a red dwarf, was treated as a potential second Earth. The media ran with the headlines, scientists gave cautiously optimistic interviews, The public imagined forests and oceans and alien sunsets under dim red skies. Then the follow-up studies started appearing, the ones that measured the star's X-ray output, the ones that modeled atmospheric loss, the ones that calculated radiation doses, and the optimism began to curdle, not into despair exactly. Scientists do not do despair, but into a kind of resigned acknowledgement that the universe does not hand out easy answers. Red dwarfs are the rulers of the galaxy. By number, by longevity, by total mass, they dominate. They are the cosmic norm. Sun-like stars are the exception. And the more we learn about red dwarfs, the more we realize that the norm is hostile. The galaxy is full of stars, more stars than anyone can count, and most of them are not friendly to life. Not because they lack planets, not because they are too far apart, but because they are too violent, too active, too prone to eruptions that strip atmospheres and sterilize surfaces. The habitable zones exist, but they are not refuges, they are battlegrounds, and the planets that orbit there are not havens. They are survivors, if they survive at all. Proxima Centauri taught us this lesson first because it is the closest. But the lesson applies to billions of others. The red dwarf next door is not special, it is typical. And if its planets are uninhabitable, then so are countless others scattered throughout the Milky Way. The search for life beyond Earth just got harder. Not impossible, but harder. Because the most common stars in the galaxy, the ones we thought might be teeming with life, are turning out to be some of the worst places to look. The universe is not hostile by design, it is hostile by accident, by physics, by the way stars work and planets form and magnetic fields tangle and snap. Red dwarfs are what they are, long-lived, abundant and violent, rulers of the cosmic realm, and their reign is not kind. The universe does not care about your hopes. That much we have established. Proxima Centauri has spent the last several billion years demonstrating this principle with ruthless efficiency, bombarding its nearest planet with enough radiation to sterilize a continent. The star flares constantly. The planet, if it ever had an atmosphere, has likely lost most of it. The surface is bathed in X-rays 250 times more intense than what Earth experiences, spiking to levels thousands of times higher during superflares. The habitable zone, that narrow band of orbital real estate where liquid water should exist, has been turned into a radiation trap. By every reasonable measure, Proxima b should be dead, lifeless. A barren rock circling a violent star, notable only for its proximity to Earth and its role as a cautionary tale about the dangers of optimism in astrobiology. And yet, there is a word that keeps appearing in scientific papers about Proxima b, even the pessimistic ones. The word is might. The planet might have retained some atmosphere. It might have subsurface water. It might have pockets of chemistry shielded from the worst of the radiation. Might is not a strong word. It is not a confident word. But it is not the word impossible either. And in a field where most exoplanets are written off as uninhabitable within a paragraph of analysis, the persistence of might is significant. It means the door is not completely closed. It means that somewhere in the back of researchers' minds there is a stubborn refusal to give up on the idea that life, somehow, could find a way. This is not wishful thinking, or rather, it is not only wishful thinking. It is based on something we have observed directly on Earth. Life does not give up easily. Life is tenacious in ways that defy reasonable expectation. You can boil it, freeze it, irradiate it, crush it under pressures that would flatten steel, starve it of sunlight, deprive it of oxygen, drown it in acid, and it survives. Not all life, not most life, but some life. Extremophiles, they are called, organisms that thrive in conditions that would kill almost anything else. And the more we study extremophiles, the more we realize that the boundaries of habitability are not where we thought they were. They are much, much wider, which raises an uncomfortable question. If life on Earth can survive in environments we once considered completely sterile, could life on Proxima b survive in an environment we have written off as uninhabitable? To answer that question, we need to start with the basics. What does life actually require? The textbook answer is liquid water, a source of energy and a reasonably stable environment. Liquid water is the solvent, the medium in which chemistry happens. Every known organism on Earth uses water, not just as a drink, but as the fundamental matrix in which biochemical reactions occur. Proteins fold in water. DNA replicates in water. Metabolism, the set of chemical reactions that keeps an organism alive, happens in water. You can imagine life based on other solvents, ammonia or methane or something more exotic, but we have never observed it. Water is the only solvent we know works. The source of energy can vary. Most life on Earth gets its energy from sunlight, either directly through photosynthesis or indirectly by eating things that photosynthesize. But not all life. There are bacteria deep underground that derive energy from chemical reactions between water and minerals. There are organisms living near hydrothermal vents on the ocean floor, where superheated water rich in dissolved minerals erupts from cracks in the seafloor, and those organisms harvest energy from the chemical gradients between the hot vent water and the cold ocean. No sunlight required. The energy is in the chemistry. The stability requirement is the tricky one. Life needs time to get started. It needs conditions that stay roughly consistent long enough for chemistry to organize itself into something that can replicate and evolve. If the environment is constantly being sterilized, if every few days the surface gets hit with a dose of radiation that breaks apart every complex molecule, then chemistry never gets the chance to become biology. The environment needs to be harsh, yes. Life can handle harsh. But it cannot handle chaotic. It cannot handle an environment where the rules keep changing faster than evolution can adapt. Proxima b fails the stability test, or at least it seems to. The flares are frequent and intense. The radiation spikes are unpredictable. The surface, if there is one, is subjected to conditions that change by orders of magnitude over the course of hours. That is chaos. That is not an environment where life can take root, but here is where the extremophiles come in. Because the more we learn about life on Earth, the more we realize that stability is negotiable. Life does not need a calm environment, it needs a refuge, a place where the chaos is blocked, or at least dampened, long enough for survival strategies to evolve. And Proxima b, for all its hostility, might have refuges. Start with radiation tolerance. The most radiation-resistant organism on Earth is a bacterium called Deinococcus radiodurans. It was discovered in the 1950s in a can of irradiated ground meat that was supposed to have been sterilized. The meat spoiled anyway because Deinococcus radiodurans was still alive inside it, happily reproducing despite being exposed to radiation doses that would kill a human almost instantly. The bacterium can survive exposure to 5,000 times the radiation dose that would be lethal to a human. 5,000 times. It does this by having multiple copies of its genome and an incredibly efficient DNA repair mechanism. When radiation breaks its DNA into hundreds of fragments, the bacterium just puts it back together. It takes a few hours, but it works. The organism is so good at surviving radiation that it has been found living inside nuclear reactors. Deinococcus radiodurans proves that life can evolve defenses against radiation if the selective pressure is strong enough. On Earth, that pressure comes from natural sources: cosmic rays, radioactive minerals in the soil, occasional bursts of solar radiation. On Proxima b, the pressure would be vastly higher, but the principle is the same. If life could get started, if it could survive long enough to evolve, radiation resistance is not impossible. It is difficult. It requires redundancy, multiple copies of genetic material, efficient repair systems, protective pigments that absorb harmful wavelengths, thick cell walls, maybe even colonies that shield interior cells while sacrificing the outer layers. All of this is plausible. All of this exists in some form on Earth. The problem is not whether radiation resistance is possible. The problem is whether life could get started in the first place. Deinococcus radiodurans evolved on a planet with a thick atmosphere, a magnetic field, and a stable sun. It evolved radiation resistance in response to environmental pressures, but it did not start out radiation resistant. It started as a normal bacterium and evolved the defenses over millions of years. Proxima b does not offer that grace period. The radiation is there from day one. Any life trying to get started would be bombarded immediately. The chemistry that leads to the first self-replicating molecules, the RNA world, or whatever prebiotic soup you imagine, requires complex organic molecules to form and persist. Radiation breaks those molecules apart. So how do you bootstrap life in an environment where the building blocks keep getting destroyed? The answer, if there is one, is depth. Radiation does not penetrate infinitely. X-rays can punch through thin atmospheres and thin layers of rock, but they are stopped by thick layers. Water is an excellent radiation shield. A few meters of liquid water can block most X-rays and a significant fraction of high-energy ultraviolet light. Ice works too, though not quite as well. Rock works even better. A few tens of meters of solid rock will stop almost anything short of cosmic rays. If Proxima b has subsurface water, oceans or lakes or aquifers buried beneath kilometers of ice or rock, then those environments would be shielded. The flares raging on the surface would not reach them. Chemistry could happen. Life could start. This is not a new idea. Subsurface oceans are considered one of the most promising environments for life in the solar system. Europa, one of Jupiter's moons, has an ocean of liquid water beneath a thick ice shell. Enceladus, one of Saturn's moons, has the same. Both are considered potential habitats for life, not because their surfaces are hospitable, but because their subsurface oceans are protected. The ice above them is tens of kilometers thick. The radiation from Jupiter and Saturn, which is intense, does not reach the water below. If life exists on Europa or Enceladus, it would be living in the dark, deriving energy from chemical reactions between the water and the rocky seafloor, completely cut off from the chaos above. Proxima b could have something similar. If the planet formed with significant water content, and if it has a rocky core, then tidal heating from Proxima Centauri's gravity could keep a subsurface ocean liquid even if the surface is frozen. Tidal heating is the same process that keeps Europa's ocean from freezing. As the planet orbits, the star's gravity squeezes and stretches it, generating friction in the interior. That friction produces heat. Enough heat to melt ice, enough heat to drive hydrothermal activity on the ocean floor, enough heat potentially to support life. The big if is whether Proxima b actually has a subsurface ocean. We do not know. We cannot observe the planet's interior. We can only model it based on what we know about its mass, radius, and orbital dynamics. The models are inconclusive. Some suggest that a subsurface ocean is plausible. Others suggest that the planet lost too much water early in its history for a deep ocean to exist now. It depends on how much water the planet started with, how efficient the atmospheric erosion was, and whether volcanic outgassing has been replenishing the water over geological time. All of these are unknowns. If a subsurface ocean exists, it would be dark. No sunlight penetrates kilometers of ice and rock. Life there would have to rely on chemosynthesis, the process by which organisms derive energy from chemical reactions rather than light. On Earth, chemosynthetic life is common near hydrothermal vents. Bacteria and archaea oxidize hydrogen sulfide or methane or other reduced compounds, extracting energy from the chemical bonds. Those bacteria form the base of an entire ecosystem. Tube worms, clams, crabs and fish all live near the vents, feeding on the bacteria or on each other. The entire food web runs on chemistry, not sunlight. If Proxima b has hydrothermal vents on its ocean floor, and if it has the right minerals dissolved in the water, then chemosynthetic life could exist there. Blind, slow, simple, but alive. There is another possibility. Even if the surface is hostile, even if the atmosphere has been mostly stripped away, there might be pockets where conditions are more forgiving. The Terminator Zone, the narrow band running around the planet where day meets night, is one such pocket. The temperatures there are moderate. The star hangs low on the horizon, providing some light but not the full intensity of the subsolar point. The radiation is still high, higher than Earth by a wide margin, but not as catastrophic as the day side. If there is any liquid water on the surface, it would be concentrated in the Terminator Zone, and if there is any surface life, it would be there too. Life in the Terminator Zone would face challenges Earth life does not. The light from Proxima Centauri is mostly in the red and infrared. Photosynthesis as we know it, the process plants use to convert sunlight into chemical energy, relies on specific wavelengths of light. Chlorophyll, the pigment that makes plants green, absorbs light most efficiently in the blue and red parts of the spectrum. Proxima Centauri's light is weighted toward the red and infrared, which means photosynthesis would be less efficient, but not impossible. There are organisms on Earth that photosynthesize using infrared light. Certain bacteria near hydrothermal vents and in deep ocean layers use bacteriochlorophyll, a variant of chlorophyll, to capture near-infrared wavelengths. If photosynthesis can work in the near-infrared, then in principle it could work under a red dwarf star. The other challenge is the flares. Even in the Terminator Zone, even with some protection from the worst of the radiation, the flares still hit. Every day or two, the X-ray flux spikes. Surface organisms would need defenses. Maybe they burrow during flares, hiding underground until the radiation subsides. Maybe they have thick protective coatings that absorb the X-rays before they reach vulnerable cellular machinery. Maybe they are colonial organisms with outer layers that die and are replaced, shielding the interior cells. All of these strategies exist on Earth in different forms. UV-resistant bacteria produce pigments that absorb ultraviolet light. Biofilms form layered communities where the top layers protect the ones below. Colonial organisms like corals have structures where individual polyps can be lost without killing the colony. Adaptations exist. The question is whether the selective pressure on Proxima b would be strong enough to drive those adaptations before the environment killed everything. There is one more refuge worth considering. If Proxima b has a thick atmosphere, much thicker than Earth's, it could act as a radiation shield even on the surface. Earth's atmosphere protects us by absorbing X-rays and ultraviolet light in the upper layers. The ionosphere, the region about 100 kilometers above the surface, is where most of that absorption happens. If Proxima b has an atmosphere 10 or 20 times thicker than Earth's, it could absorb more radiation, bringing surface doses down to levels that are harsh but not immediately lethal. A thick atmosphere would also help with heat transport, preventing the extreme temperature gradients that would otherwise make the planet uninhabitable. The problem is that a thick atmosphere is hard to maintain around a flaring red dwarf. The same radiation that the atmosphere is supposed to block is also eroding the atmosphere over time. It is a race between atmospheric replenishment from volcanic outgassing or cometary impacts and atmospheric loss from radiation and stellar wind. If replenishment wins, the atmosphere survives. If loss wins, it does not. We do not know which side is winning on Proxima b. Observations of the planet's atmosphere are extremely difficult. The planet does not transit its star from our perspective, which means we cannot use transmission spectroscopy, the technique that lets astronomers analyze the composition of exoplanet atmospheres by watching starlight filter through them during a transit. The planet is also too close to its star for direct imaging with current telescopes. We can infer some things from models, but the models are only as good as the assumptions we feed into them. Different assumptions lead to different conclusions. Some models say the atmosphere is gone. Others say it might still be there, clinging on, eroded but not destroyed. The uncertainty is frustrating, but it is also a reminder that we are still at the beginning of this story. The data we need to answer these questions does not exist yet. What we do have is a growing catalogue of extremophiles on Earth that keep pushing the boundaries of what we think life can tolerate. Tardigrades, microscopic animals also known as water bears, can survive temperatures close to absolute zero and as high as 150 degrees Celsius. They can withstand pressures 6 times greater than those in the deepest ocean trenches. They can survive in the vacuum of space, exposed to solar radiation for days. They do this by entering a state called cryptobiosis, where they essentially shut down all metabolic activity, expel most of their water content, and wait. When conditions improve, they rehydrate and resume normal activity. They are not immortal. They can be killed, but their ability to survive extreme conditions is unmatched by any other complex organism on Earth. Then there are the archaea living in the deep subsurface, kilometers below the surface, in rock formations where temperatures reach 120 degrees Celsius and pressures are crushing. There are microbes that have been cut off from the surface for millions of years. They metabolize hydrogen gas produced by reactions between water and minerals in the rock. They reproduce slowly, perhaps once every 1,000 years or more. Their existence proves that life does not need sunlight, does not need a surface, does not need anything resembling the conditions we associate with habitability. It just needs liquid water and a source of chemical energy. Everything else is optional. The discovery of extremophiles has fundamentally changed how astrobiologists think about habitability. Before extremophiles were well understood, the assumption was that life required Earth-like conditions, a stable star, a protective atmosphere, a magnetic field, moderate temperatures, liquid water on the surface. The habitable zone was narrowly defined. Then we found bacteria in boiling hot springs, archaea in frozen Antarctic lakes, fungi growing inside nuclear reactors, life in acid mine drainage with pH levels low enough to dissolve metal. Every new discovery expanded the range of conditions where life could exist. The habitable zone, it turned out, was not a narrow band. It was a broad spectrum, and the more we looked, the broader it got. Proxima b sits at the extreme edge of that spectrum. The radiation environment is worse than anything on Earth. The flares are more frequent. The atmospheric erosion is more severe. The tidal locking creates temperature extremes that Earth never experiences. But the question is not whether Proxima b is Earth-like. It is not. The question is whether the conditions on Proxima b, extreme as they are, fall within the expanded range of habitability that extremophiles have shown us is possible, and that question does not have a clear answer yet. There is ongoing research into how life might survive under extreme radiation. In 2021, a team at the University of Vienna exposed colonies of the fungus Cryomyces antarcticus to simulated Martian conditions, including high levels of ultraviolet radiation. The fungus survived. It did not thrive, but it survived. Its cell walls darkened, producing melanin, a pigment that absorbs UV light and protects the cells beneath. After months of exposure, the fungus was still viable. When returned to normal conditions, it resumed growth. The experiment suggests that even complex organisms, not just bacteria, can evolve defenses against radiation if the selective pressure is present. Another line of research focuses on how life might use radiation as an energy source. There is a fungus called Cryptococcus neoformans that was found growing inside the damaged reactor at Chernobyl. It was not just surviving the radiation, it was thriving. Researchers discovered that the fungus uses melanin to capture energy from gamma rays, converting that energy into chemical energy through a process that resembles photosynthesis but uses radiation instead of visible light. The mechanism is not fully understood, but the implications are profound. If life can harvest energy from radiation, then a high radiation environment is not a death sentence, it is a resource. Proxima b, from that perspective, is not a wasteland. It is an energy-rich environment where radiation-eating life could flourish. This is speculative, very speculative. The radiation levels on Proxima b are orders of magnitude higher than what Cryptococcus neoformans experiences at Chernobyl, and the fungus at Chernobyl has the advantage of being shielded by the reactor building and surrounding structures. Proxima b offers no such shielding, but the principle is there. Life can use radiation. Life can adapt to radiation. The question is whether adaptation can keep pace with the intensity and frequency of the assault. The Terminator Zone remains the most plausible location for surface life, if surface life exists at all. The temperatures are moderate. The light is dim but present. The radiation is high, but not as catastrophic as the subsolar point. If there is liquid water in the Terminator Zone, it would likely be in the form of scattered pools or thin layers of moisture rather than large oceans. Life there would be microbial, probably forming biofilms on rocks or in shallow depressions where water accumulates. Photosynthesis might be possible using bacteriochlorophyll adapted to red and infrared light. Chemosynthesis might be more reliable, drawing energy from minerals dissolved in the water. The organisms would need to be radiation resistant. They would need to tolerate high winds, which models predict would be constant along the Terminator. They would need to deal with the fact that the sun never moves, which means no day-night cycle, no circadian rhythm, no variation in light intensity. It is a harsh, static environment. But harsh and static is not the same as impossible. One of the frustrating aspects of this discussion is how much of it is hypothetical. We have no direct evidence of life on Proxima b. We have no direct evidence of an atmosphere. We have no direct evidence of surface water. What we have are models, simulations, and extrapolations from what we know about extremophiles on Earth. That is not nothing. Models are useful. They help us understand what is possible, what is plausible, and what is outright impossible. But they are not observations. And in science, observations are what matter. Until we can point a telescope at Proxima b and measure its atmosphere, its surface composition, its temperature distribution, we are guessing. Educated guessing, but guessing nonetheless. The next generation of telescopes might change that. The James Webb Space Telescope is already providing unprecedented views of exoplanet atmospheres. Future missions, like the Habitable Worlds Observatory proposed by NASA, would be specifically designed to study rocky planets in the habitable zones of nearby stars. Proxima b would be a prime target. If the planet has an atmosphere, these telescopes could detect it. If the atmosphere contains oxygen, methane, or other biosignature gases, they could measure those too. A detection of oxygen would not prove life exists, but it would be a strong hint. Oxygen is reactive. It does not stay in an atmosphere for long unless something is constantly replenishing it. On Earth, that something is photosynthesis. If Proxima b has oxygen in its atmosphere, something is producing it. But that is years away, maybe decades. For now, the question of whether life can survive Proxima's rages remains unanswered. The evidence from extremophiles suggests it is not impossible. The models suggest that refuges might exist, subsurface oceans, the terminator zone, a thick protective atmosphere. The radiation tolerance demonstrated by organisms like Deinococcus radiodurans shows that life can evolve defenses if given the chance. The fungus at Chernobyl shows that life can even harvest energy from radiation. None of this proves life exists on Proxima b, but it keeps the door open. It keeps the word might alive in the scientific literature. Life is tenacious. That is not a sentimental statement. It is an observation. Life on Earth has survived 5 mass extinctions. It has colonized every niche, from deep ocean trenches to high mountain peaks to the insides of rocks kilometers underground. It has adapted to extremes of temperature, pressure, acidity, salinity, and radiation. It has found ways to survive in places we once assumed were sterile. Every time we think we have found the limit, we discover life has already crossed it. The boundaries keep moving. The definition of habitability keeps expanding. And somewhere in that expanding definition, there might be room for a planet like Proxima b. The universe does not care about your hopes, but life, it seems, does not care about the universe. Life is stubborn. Life is persistent. Life finds a way, not because it is lucky, but because it is relentless. It tries every possible strategy, and the ones that work survive. The ones that do not work die. Over billions of years, that process has produced organisms that can survive almost anything. Whether it can produce organisms that can survive Proxima Centauri is the question we are left with, and the answer, frustratingly, is that we do not know. Not yet. But the fact that we are asking the question, the fact that scientists are taking it seriously, the fact that the word might keeps appearing in the research papers suggests that the universe's cruelty has limits. Those limits are wide, wider than we once thought. Wide enough, maybe, to include a radiation-soaked rock orbiting a violent red dwarf 4.24 light-years from here. Wide enough, maybe, for life. Not life as we would recognize it, not forests and oceans and blue skies, but life nonetheless, clinging to existence in the cracks and shadows, surviving, adapting, refusing to die, because that, in the end, is what life does. It refuses, and until we prove it cannot survive on Proxima b, we have to accept the possibility that somewhere in the terminator zone, or deep beneath the surface, something might be alive. Tenacious, relentless, defiant, holding on, against all odds, against all reason. Life. The universe has handed us a laboratory, 4.24 light-years from Earth, close enough that we can actually study it in detail, far enough that we will never visit it in our lifetimes, sits a star system that refuses to behave the way we hoped it would. Proxima Centauri and its planet Proxima b have become the test case for everything we thought we knew about habitable worlds. And the results of that test are not what anyone wanted. Not the scientists who discovered the planet in 2016 with such excitement, not the astrobiologists who spent years imagining what life might look like under a dim red sun, not the public who briefly allowed themselves to believe that the nearest exoplanet might be a second Earth. The test results are clear. Proxima b is not habitable. Not in any conventional sense, not by any standard that includes breathable air, liquid water on the surface, or an environment where chemistry can organize itself into biology without being immediately destroyed. The planet is a radiation zone, the star is a flare machine, and the combination of the two has created conditions so hostile that even talking about habitability feels like a stretch. The word itself starts to lose meaning when you apply it to a world bathed in X-rays 250 times more intense than what Earth receives, spiked every day or two by superflares that would sterilize a continent. This is where we are. 8 years after the discovery, hundreds of research papers later, the optimism has drained out of the conversation. Not completely. There are still scientists who will argue that life might exist in subsurface oceans, or in the Terminator zone, or in some configuration we have not thought of yet, and they might be right. The door is not completely closed, but it has been pushed most of the way shut, and what little light is coming through is dim and red and not particularly encouraging. Proxima Centauri has taught us lessons, hard lessons, uncomfortable lessons, the kind that force you to rewrite your assumptions and start over with a clearer, colder understanding of how the universe actually works. These lessons matter because Proxima is not unique, it is typical, and the implications of that ripple outward through the entire field of exoplanet science, reshaping how we think about where life might exist and where we should be looking. Start with the most obvious lesson. Being in the habitable zone is not enough. For decades, the habitable zone was treated as a kind of cosmic sweet spot. Find a planet in that narrow band of orbital distances where liquid water could theoretically exist, and you had a candidate for life. The calculation was simple. Too close to the star and water boils away. Too far and it freezes. In the middle, just right. Goldilocks logic. It worked beautifully for sun-like stars. Earth sits in the middle of the sun's habitable zone, and Earth is teeming with life. The math checked out. The concept was clean. Astronomers used it as the first filter when evaluating newly discovered exoplanets. Is it in the habitable zone? Yes or no? If yes, interesting. If no, move on. Proxima b sits in the habitable zone, dead center by the traditional calculation. The energy flux reaching the planet matches what Earth receives from the sun. The temperatures, at least in theory, should allow for liquid water. By every metric that defined habitability for the last 50 years, Proxima b qualified, and yet the planet is almost certainly uninhabitable. The habitable zone did not lie, it just did not tell the whole truth. The calculation accounted for total energy. It did not account for the spectrum of that energy. It did not account for stellar activity. It did not account for flares. It did not account for X-rays. It treated the star as a passive heat source, a lamp that you could move closer to or farther from to adjust the temperature. That simplification works for stable stars. It fails catastrophically for active ones. Red dwarfs are not stable. They are magnetically chaotic. Their fully convective interiors generate twisted, tangled magnetic fields that snap and release energy in flares. Those flares produce radiation across the spectrum, but especially in the high-energy bands, X-rays and extreme ultraviolet light. The wavelengths that ionize atmospheres, break apart molecules and sterilize surfaces. The habitable zone around a red dwarf sits close to the star, within 10 million kilometers or less, because the star is so dim. At that distance, the inverse square law works against you. The radiation intensity is not just proportionally higher, it is catastrophically higher. Proxima b receives 250 times more X-rays than Earth during quiet periods. During flares, thousands of times more. That is not a habitable environment, that is a bombardment zone. The lesson is that the habitable zone needs to be redefined, not abandoned, redefined. Temperature still matters, liquid water still matters, but they are not sufficient conditions. You also need a radiation environment that does not constantly undo whatever chemistry is trying to happen. You need a star that is not actively hostile, and you need to account for stellar activity as a first-order effect, not an afterthought. The new definition of a habitable zone is narrower, more restrictive, and it excludes a lot of planets that the old definition would have counted. Proxima b is the case study, the example that broke the model, and every red dwarf system in the galaxy is now being re-evaluated in light of what we learned from Proxima. The second lesson is about red dwarfs themselves. For years, they were considered prime candidates for hosting life. They are abundant, making up 70% of all stars in the galaxy. They are long-lived, burning their hydrogen fuel slowly enough to remain stable for trillions of years. Their habitable zones are close in, which makes planets easier to detect with current techniques. Everything about red dwarfs suggested they should be hotbeds of life. The logic seemed bulletproof. If the galaxy is full of red dwarfs, and red dwarfs live forever, then surely some of their planets have developed life by now. Proxima Centauri has forced a reckoning with that logic. The abundance of red dwarfs is not an advantage, it is a problem. Because if most red dwarfs behave like Proxima, and the evidence suggests they do, then the habitable zones around 70% of the galaxy's stars are not habitable. They are death traps. This is not pessimism, this is data. Survey after survey has shown that red dwarfs, especially the smaller and cooler ones, are flare stars. They erupt constantly. Some are more active than others, but the baseline level of activity is far higher than Sun-like stars, and the activity does not taper off with age. Sun-like stars are more active when they are young, then calm down as they age and lose angular momentum. Red dwarfs stay active for billions of years. Proxima Centauri is about 4.8 billion years old, roughly the same age as the Sun. The Sun is calm now. Proxima is not. It is still flaring, still bombarding its planets, and it will keep doing that for billions more years. There is no grace period, no era of stability where planets can develop atmospheres and hold on to water and give life a chance. The violence is constant, the assault is unending, and any planet sitting in the habitable zone takes the full brunt of it. The implications are staggering. If red dwarf habitable zones are largely uninhabitable, then the number of potentially habitable worlds in the galaxy just dropped by at least half. Maybe more. The search for life suddenly got a lot harder, not impossible, but harder. Sun-like stars, the ones that are calm and stable and produce most of their energy in the visible spectrum, make up only about 7% of the galaxy. If those are the only stars that can reliably host habitable planets, then the number of targets for future missions shrinks dramatically. The Habitable Worlds Observatory, NASA's planned successor to the James Webb Space Telescope, is being designed to study rocky planets around nearby stars. Proxima b was supposed to be one of the prime targets. It still is, but not because anyone expects to find life there. It is a target because we need to confirm how bad the situation actually is. We need to measure the atmosphere, or the lack of one. We need to see what happens to a planet after billions of years of flare bombardment. Proxima b is no longer the hopeful case. It is the cautionary tale. The third lesson is about tidal locking. When a planet orbits close enough to its star, tidal forces lock its rotation to its orbit. One side faces the star permanently, the other side faces away. There is no day-night cycle, no rotation to distribute heat evenly across the surface. The result is extreme temperature gradients, with one hemisphere roasting and the other freezing. For years, astronomers debated whether tidal locking was a deal-breaker for habitability. Some argued that a thick atmosphere could transport heat from the day side to the night side, smoothing out the extremes. Others pointed out that tidal locking would weaken or eliminate a planet's magnetic field, leaving it vulnerable to stellar wind and radiation. Proxima b has not settled that debate, but it has shifted the weight of the evidence. Tidal locking is not an automatic disqualifier, but it makes everything harder. The terminator zone, the narrow band where day meets night, might be habitable in theory, but in practice that zone would be hammered by winds, scoured by radiation, and subjected to conditions that change dramatically over short distances. Walking a few hundred kilometers in any direction would take you from moderate temperatures to either scorching heat or freezing cold. That is not a stable environment. That is a knife edge. The combination of tidal locking and high radiation is particularly lethal. Tidal locking reduces the planet's ability to generate a magnetic field. Without a strong magnetic field, the planet cannot deflect the stellar wind. Without that deflection, the atmosphere erodes, and without an atmosphere there is no heat transport. The day side becomes an oven, the night side becomes a freezer, and the terminator, the only potentially habitable zone, becomes an ever-shrinking strip where conditions are barely tolerable. Proxima b, if it is tidally locked as models predict, faces all of these problems simultaneously. The tidal locking weakens its defenses, the radiation exploits that weakness, and over billions of years the planet is stripped bare. This has implications beyond Proxima. Tidal locking is common for planets in red dwarf habitable zones because those zones are so close to the star. The tidal forces at that range are strong. The locking happens fast, within the first few 100 million years. That means most habitable zone planets around red dwarfs are tidally locked. And if tidal locking is a major obstacle to habitability, then most habitable zone planets around red dwarfs are not habitable. Again, the numbers keep shrinking. The galaxy is full of planets, but the fraction of those planets where life could actually arise and survive is starting to look vanishingly small. The fourth lesson is about what we mean when we talk about life. For a long time, the assumption was that life required Earth-like conditions, a breathable atmosphere, liquid water on the surface, sunlight for photosynthesis, moderate temperatures, a stable star. The more we study extremophiles on Earth, the more we realize that those assumptions are too narrow. Life can survive in boiling water, in frozen deserts, in acidic lakes, in the lightless depths of the ocean, in rock kilometers underground. Life adapts, it evolves defenses, it finds niches. The boundaries of habitability are wider than we thought, but they are not infinite. There is a limit, and Proxima b might be past that limit, or it might not. That uncertainty is maddening, but it is also the point. We do not know where the limit is. We thought we did. Proxima is teaching us that we were wrong. If life exists on Proxima b, it would have to be nothing like life on Earth. Not in terms of biochemistry maybe, but in terms of environment. It would have to survive in perpetual twilight or total darkness. It would have to tolerate radiation doses that would kill anything we know. It would have to endure flares that spike the radiation by factors of thousands without warning. It would have to do all of this without the moderating influence of a thick atmosphere, a protective magnetic field, or a stable climate. That is a tall order. Maybe too tall. But the fact that we are even asking the question, the fact that scientists are taking seriously the possibility that life could exist in subsurface oceans or radiation-shielded caves or along the Terminator, shows how much our thinking has evolved. The definition of life-sustaining is expanding, not because we want it to, because the universe keeps showing us organisms that survive in places we assumed were sterile. Proxima Centauri is forcing us to confront a harder question. Is habitability binary, or is it a spectrum? The old model treated it as binary. A planet is either habitable or it is not. If it is in the habitable zone and has the right conditions, life can arise. If it is not, life cannot. Clean and simple. Proxima b suggests that habitability is a spectrum. The planet is not completely uninhabitable. There are scenarios, unlikely but not impossible, where life could exist. Subsurface oceans, Terminator zones, thick atmospheres, radiation-resistant organisms. Each of these scenarios requires a long chain of favorable conditions, and each link in that chain is uncertain. But the scenarios are not ruled out. They are just improbable. Proxima b sits somewhere in the grey zone between definitely uninhabitable and potentially habitable, and that grey zone is uncomfortable. It does not give us clean answers. It gives us probabilities and uncertainties and a growing list of things we need to measure before we can say anything definitive. The fifth lesson is about the search itself. For decades, the strategy has been to find Earth-like planets around Sun-like stars. That makes sense. Earth is our only example of a planet with life. The Sun is our only example of a star that can host such a planet. If you are looking for something and you only have one example to work from, you look for more things like that example. It is a sound strategy, but it is also limiting. Sun-like stars are rare. Only 7% of the galaxy. If you restrict your search to Sun-like stars, you are ignoring 93% of the stellar population. Red dwarfs are everywhere. They are the dominant type of star. If you could prove their planets were habitable, the number of potential targets would explode. But Proxima has shown that red dwarf planets are probably not habitable, at least not in the conventional sense. So where does that leave the search? One option is to focus on older, quieter red dwarfs. Not all red dwarfs are equally active. Some are calmer than Proxima, some have lower flare rates. If you could identify the subset of red dwarfs that are less violent, their planets might have a better chance. The problem is that even the quietest red dwarfs are more active than the Sun, and their habitable zones are still close in, which means the radiation intensity is still high. You are not eliminating the problem, you are just reducing it. Whether that reduction is enough to make a difference is an open question. Another option is to look for planets with unusually strong magnetic fields or unusually thick atmospheres. Both of those could provide protection against the stellar wind and flares. The challenge is that we cannot measure magnetic fields or atmospheric thickness for most exoplanets. The techniques do not exist yet. We can infer some things from models, but models are not observations. What we need are direct measurements. And that requires better telescopes, longer observation times, and a lot of patience. A third option is to redefine the target. Maybe we should not be looking for Earth-like planets. Maybe we should be looking for planets with subsurface oceans, worlds like Europa or Enceladus, where the surface is hostile but the deep interior is protected. Those planets would not show obvious signs of life from a distance. No oxygen in the atmosphere, no vegetation reflecting light in characteristic wavelengths. But if we could detect plumes of water vapor erupting from the surface, or if we could measure the thickness of an ice shell, we might be able to infer that a liquid ocean exists below. And where there is liquid water and a source of energy, there is at least the possibility of life. This approach broadens the search. It also makes it harder. Subsurface oceans are difficult to detect and even more difficult to study. But Proxima b and the lessons it has taught us suggest that this might be where we need to focus. The sixth lesson is philosophical. Does life find a way no matter the cost, or are there environments so hostile that life simply cannot take hold? Proxima b does not answer that question. It poses it. If we eventually confirm that the planet is lifeless, that tells us something important. It tells us that there are limits, that the universe contains places so violent, so chaotic, so saturated with radiation that even the hardiest extremophiles cannot survive. It tells us that habitability is not just about having the right ingredients. It is about having the right conditions, sustained over long enough periods for chemistry to organize itself into something that can replicate and evolve. If Proxima b had life, that would tell us something even more important. It would tell us that life is more resilient than we imagined, that the boundaries of habitability extend further than we thought, that even a radiation-soaked rock orbiting a flare star can support biology if the biology is tough enough. Either answer changes how we think about life in the universe. Either answer is profound. For now, we do not have an answer. What we have is data. Observations of the star, models of the planet, measurements of the radiation environment, simulations of atmospheric loss. All of it points in the same direction. Proxima b is almost certainly uninhabitable by conventional standards, but almost certainly is not the same as definitely. And that gap, that narrow sliver of uncertainty, is where hope and curiosity live. It is where the next generation of telescopes will focus their instruments. It is where the next wave of research papers will direct their attention. Because even if the answer turns out to be no, even if Proxima b is confirmed to be a barren, airless rock, the process of getting to that answer will teach us things we did not know. It will refine our models. It will sharpen our understanding of how stars and planets interact. It will give us a baseline for evaluating other red dwarf systems. Proxima Centauri, for all its hostility, is a gift. Not the gift we wanted, but a gift nonetheless. The future of Proxima, the star itself, is straightforward. It will keep burning for trillions of years. Long after the Sun has exhausted its hydrogen and become a white dwarf, Proxima Centauri will still be on the main sequence, fusing hydrogen in its core, radiating dimly in the infrared. It will keep flaring. The violence will not stop. The magnetic fields will keep twisting and snapping. The X-rays will keep pouring out. And Proxima b, if it survives that long, will keep orbiting, tidally locked, irradiated, barren. A monument to the fact that proximity is not the same as hospitality. The future of our understanding, on the other hand, is less clear. We are at the beginning of this story, not the end. The discovery of Proxima b in 2016 was the opening chapter. The follow-up studies, the flare observations, the atmospheric models, those were the middle chapters. The part where the optimism faded and the reality set in. But the conclusion has not been written yet. We have not observed the planet's atmosphere directly. We have not confirmed whether it has water. We have not ruled out the possibility of subsurface life. All of that is still to come. The James Webb Space Telescope is already observing other exoplanets, analyzing their atmospheres, detecting molecules. Proxima b is on the list. So are other planets around red dwarfs. Each new observation adds a piece to the puzzle. Each new measurement refines the picture. And slowly, over years and decades, the uncertainty will shrink. The gray zone will narrow. And we will know with confidence whether Proxima b is completely lifeless or whether some improbable pocket of chemistry has managed to cling to existence despite everything the star has thrown at it. The broader lesson, the one that reaches beyond Proxima and touches every exoplanet survey, every search for biosignatures, every mission designed to find life beyond Earth, is this: the universe is not built for our convenience. It does not care about our hopes or our definitions or our assumptions. It operates by rules that predate us, that will outlast us, and that do not bend to accommodate our expectations. For years, we thought the habitable zone was a shortcut, a simple filter that would narrow the search and point us toward the most promising candidates. Proxima Centauri has shown us that the shortcut does not work. Being in the habitable zone is necessary but not sufficient. You also need a star that is not trying to kill you. And most stars, it turns out, are trying to kill you. Not maliciously, just by existing. By doing what stars do. Red dwarfs flare because they are fully convective. That is not a design flaw. That is just physics. But the consequence is that their habitable zones are hostile, and that hostility has to be accounted for. Not dismissed, not ignored, accounted for. The search for life beyond Earth is not getting easier. Proxima Centauri has made that clear. But it is getting more honest. We are asking harder questions. We are demanding better answers. We are no longer satisfied with a planet being in the habitable zone. We want to know about the star's activity. We want to measure the planet's atmosphere. We want to understand the radiation environment. We want to see the data. And Proxima b, for all its disappointments, is teaching us what data to look for and how to interpret it. It is teaching us that habitability is not a checkbox. It is a balance, a precarious, fragile balance between a planet's defenses and a star's assault. And most of the time, the star wins. That is not the ending anyone wanted when Proxima b was discovered, but it is the ending the data has given us. And in science, you do not get to choose your endings. You follow the evidence. You accept the conclusions, even when they are uncomfortable. You move forward with a clearer understanding of how the universe actually works, not how you wished it worked. Proxima Centauri is 4.24 light-years away, close enough to study, far enough to be safe from its violence. It sits there, flaring into the void, indifferent to whether we find its planets habitable or not. The star does not care. The planet, if it could care, probably would not either. They are just objects, governed by physics, playing out a story that started billions of years ago and will continue for trillions more. We are the ones watching. We are the ones asking questions. And the answers we are getting are teaching us humility, teaching us caution, teaching us that the universe is full of planets, but habitable planets are rare. Rarer than we hoped. Harder to find than we expected. And the nearest one, the one we thought might be a second Earth, turned out to be a lesson in everything that can go wrong. That is what Proxima teaches us. That is the gift our nearest hell has given us. Not hope, not confirmation, but clarity. Cold, sharp, undeniable clarity. And in the long run, that might be more valuable than hope ever was. 4.24 light-years. That is all that separates us from the nearest star beyond our own. Close enough to measure, close enough to study, close enough that when we discovered a planet orbiting that star, the headlines wrote themselves: Proxima b, Earth-sized, habitable zone. Potentially habitable. For a moment, the universe felt smaller, less lonely. The idea that we might have neighbors, real neighbors, close enough to matter, close enough to one day reach, sat in the mind like a promise. Then the data came in, and the promise turned into a warning. Proxima Centauri taught us that proximity is not the same as hospitality. That being in the habitable zone does not guarantee habitability. that the most common stars in the galaxy, the red dwarfs that outnumber every other type by factors of 7 to 1, are not gentle, they are violent. Their habitable zones are not refuges, they are bombardment zones. And the planets orbiting there, the ones that should have been teeming with life, the ones we hoped would answer the oldest question humanity has ever asked, are probably barren, stripped, sterilized by the very stars they orbit. This is not the story we wanted, but it is the story the universe gave us. And maybe that is the real lesson. The universe does not owe us habitable worlds. It does not owe us life beyond Earth. It does not owe us anything. What it gives us instead is honest. It gives us data. It gives us observations. It gives us the truth, whether we like it or not. And the truth, written in X-rays 250 times brighter than anything Earth has ever faced, delivered across 4.24 light-years of empty space, arriving now, says this: the search is harder than we thought. The targets are rarer, the boundaries are narrower, and the universe, for all its vastness, for all its billions of stars and trillions of planets, is not built for our convenience. Proxima Centauri sits out there, flaring into the void, indifferent, relentless, the nearest star, the nearest hell, and it has been trying to tell us something since the moment we looked closely enough to listen. Not all doors lead somewhere welcoming. Some doors, even the ones closest to home, open onto nothing but radiation and despair. That does not mean we stop looking. It means we look harder, smarter, with clearer eyes and fewer illusions. Because if the nearest exoplanet taught us anything,